All right, let's go ahead and begin. Welcome, everyone. Thanks a lot for joining us this evening. Um, we have an exciting presentation for everyone tonight. It's titled Analog Tape Playback Without WoW and Flutter by John Chester and Jamie Howarth from Plangent Processes Incorporated. I'm really excited about learning a lot tonight from both John and Jamie, and excited to learn more about the Plangent process. I did want to make a couple announcements regarding our meeting for next month. Next month on November 21st at 6 p.m., we are hosting a meeting hosted by Dan Mortensen and Lawrence Schwedler, focusing on concurrent meetings and what the future looks like for concurrent meetings using both a live in-person building and room, but also a Zoom meeting. And I know that Dan and Lawrence are working very diligently and hard to make sure that this meeting is impressive for both the people that are in person at our meeting, and also for the people that want to attend online. This is going to be historic for us because this is going to be our first attempt at trying to do a concurrent meeting in our section's history. So I hope that you'll consider joining us again November 21st next month at 6 p.m. while we learn about the ins and outs of concurrent meetings, as well as a couple mini presentations, or in fact, I think I misspoke there. Not mini presentations, but some presentations as well. And Dan, did you want to say a few words about next month's meeting?
Yeah, definitely. Please. Thank you. So it's going to be just one presentation, and that's Ian Shores, who is affiliated with some kind of gaming audio company, I think. And
That's
Lawrence
correct.
said,
Highwire Games.
yeah, and tell us what he does.
So
Are
Ian
you
is
able
the
to?
audio director for Highwire Games, and he is working on a new title with that group. And my impression is that Ian is going to be talking about some of the approaches that they're taking to more things more on the spatial audio side. So I'm not sure if it's virtual reality that they're doing, or if they're doing a first person kind of game. But from my understanding, the spatial element is a big part of what Ian is going to be talking about.
Yeah, and he's a graduate of DigiPen apparently, and that is something that DigiPen does. And Lawrence says that what Ian is doing is real cutting edge and real exciting to people in that world. So that is going to be our nominal topic, and that'll be a regular meeting. And then the other part of the topic will be how we achieve our goal of having the people who are present, and this will be the first meeting that we've had in person in a year and a half plus, how we make the in-person experience and the online experience as close to the same as we can. And we've been talking about it and thinking about it, and we'll see how well we succeed at doing that. So that is Sunday, November 21st, and we're having it on a Sunday because there's going to be a lot of technical setup involved in testing, and Sunday is the only day we can get at DigiPen, the big room there, uh, for as long as we need to set up and tear down each time. And for my part, I'm a PA company in real life, in theory, although I've been working a bunch lately. And 3 years ago, there was a audio for virtual and augmented reality in-person conference at DigiPen, and I was also responsible for routing the video all over the building uh, for the various rooms, and that is going to be relevant to this meeting. That experience is going to be relevant to that meeting, so that's going to be a part of it, is how well that worked. So uh, there you go. That's that's that meeting. Oh, and we're going to rehearse it. We're having a couple of dry runs ahead of time, and you'll be able to experience it either in person or online. Not the dry runs, but the actual meeting. So that's about it for that.
Great.
Right.
Thank you, Dan. I did want to make one note that if you do want to attend that meeting in person, you must be fully vaccinated, and I think provide proof of that with you when you come. And it is a mask event, so you will need to be prepared, wear a mask, get vaccinated before you come. So thanks a lot, Dan, for helping out with that. I'm excited to see how this all works.
Me too.
Okay, great. Moving on. Um, Currently, the AES is hosting a convention. Some of you may be checking that out. It's been going since the 16th. The convention is an online convention, and it takes place from October 16th to the 31st. There is a technical program they state that takes place on the 20th through the 23rd. So we encourage you to check that out and attend the convention if you have time. Next, I'm going to talk about just a couple technical things related to how our meetings run. First off, as Dan mentioned a bit earlier, we would appreciate it if you could include your full name in your Zoom. So the way that can be done is if you click on your photo or your picture, if you don't have your full name displayed, you can click on the little dots, at least on a PC. You can click on the three dots in the top right corner, and that should allow you to rename your name. And so if you could please post your full name there. We like to do that so that we can be more transparent, and so that we're talking to someone and it's not just an avatar or something. On that note, during the presentation, we'd actually appreciate your help muting your microphone as well as muting your camera during the presentation for tonight's presentation. So again, please, if you can, while our presenters are sharing their presentation, please mute your mic and mute your camera as a courtesy to the presenters. I'd also like to state that Dan Mortensen, who you've heard from already tonight, he's going to be helping us out as the MC tonight. So if you have any questions to our presenters, please post those in the chat, and Dan will forward that information while the presentation is going to our presenters at an appropriate time. So if you have questions for the presenters, please don't hesitate to ask those questions in the chat. And Dan, thank you so much for helping with the MC tonight. I'm going to turn the time over now again to Dan, and Dan is going to say a few words about his ongoing series known as Tea Time Topics. And then after that, Dan will introduce our guests. So Dan, take it away. Thanks.
All right, thanks, Greg, and thanks everybody. Thanks for coming. The Tea Time Topics thing is a thing that I came up with that we have on Saturdays generally, although we're at Mondays now because I'm working Saturdays this month. But we pick a subject and have somebody present to us about something that they're passionate about. Last time we had one was Steve Lampin talking about his 40,000 baseball cards and the influence of 1961 and 62 on his collections. And he talked about collecting in general. And previous ones that we've had have been about Woodstock with Bill Hanley, who was also an attendee at the Tea Time Topics things and is here tonight, actually. And Bob Smith, who is here tonight, has talked about stuff. And we really get into it. We spend a lot of time, and people ask questions until we're exhausted. Actually, we've never
and then we still keep going.
Yeah, and then we keep going. And Luke is part of it too. And I thought I would say, rather than me telling you why it's so great, Luke, why is it a good thing to come to? And then we'll follow it with John saying, why is it a good thing to come to? What do you enjoy about it?
Just it's a nice group of people, and we, all go around talking about interesting topics. I know when we started out, what was it, the year plus ago, whenever,
May of 2020.
yeah, a year and a half ago, there was some question about what are we going to talk about and who's going to come up with things. And, as we said, the first one, it was going to be, okay, well, these people are going to give 5-minute presentations. And I thought, well, mine might take 10 minutes. Is that going to be okay? And it's turned out that, somebody giving a presentation for an hour and a half is not uncommon, or even longer. And, the conversation just flows, and it's a nice way to spend a Saturday evening, or as of lately, Monday evening.
Or afternoon, depending on where you are.
Oh,
or
yeah. Or
midnight if you're where Gordon is in Scotland.
Yeah, or morning in the case of India.
Yeah. Yeah. And I just saw Bob Smith posted that he's going to present on November 1st. What are you going to talk about, Bob?
I think that depends on what people would like to hear from me. Maybe they don't want to hear anything. I could talk on anything technical, from measurements to psychoacoustics to audible distortion. How audible is distortion? That's one of the things I've been putting together this week.
Cool. Okay, so there's another thing. John, what do you like about coming to him? John?
Well,
you're a regular.
Really interesting group of people who know a lot of stuff about a lot of different subjects, and we end up going down some routes that you might not expect when you first hear about a particular topic, but it always ends up being really educational. So.
And the crazy thing is, even when we don't have a topic, we still talk for 4 hours about.
Right. Yes.
And it's fascinating.
I would just add that, in contrast to a meeting like this, which is typically, fairly structured, and the presenter gives their presentation, and, there may be chance for questions afterwards. Not always, but, with tea time topics, typically it's a lot looser, and people interject, and questions come and go, and tangents happen, and things like that. So things go in a lot more directions than I think anybody might expect at the beginning of the night.
Yeah, so let's call that enough of a commercial for the thing. And if you want to come to it, you should private message me here with your email, although I probably have all your emails because I'm the one who does the Eventbrite thing. But anyway, send me your email and I'll send you the link, and we'll hope to see you. The next one is going to be a week from today, and it's Matt Luton's, who, Gary, could one of you guys describe what Matt does briefly? He's a mastering guy for...
He's a mastering engineer and analog tape duplicator engineer, and does a lot of stuff for Chad Kasem at Analog Productions in Salina, Kansas.
Yeah. And he's going to give us a tour and a description and show how he does what he's doing. He's going to cut something in real time, I think, for us.
Yeah, they have Doug Sachs's mastering lab equipment, which they bought when Doug Sachs passed away in Hollywood, and they moved it to Salina, Kansas, and have been restoring it in order to do mastering there, because they got a studio there in Kansas, and they got a record pressing plant down the street. So
convenient.
Yeah.
One-stop shopping.
So that should be real interesting, and that's Monday, a week from today at 3 p.m. We start at 3 p.m. Seattle time, Pacific time, and I open the doors at 2:30 to make sure everybody can hear each other and see each other and all that stuff. And we go into the discussion at 3, and then I throw everybody out at 7 if I can. I can't always do that, but I try for 7, and sometimes we go till 7:30. And it's a fun time if you're geeky like I am, and we are. So that's enough of that. And for latecomers, the reason you're seeing this diagram on the stage is, or on the screen, is because the playback is complex, and Zoom doesn't seem to do the same thing. You don't seem to get the same result from Zoom once you get it working if you leave it necessarily. So we're leaving this ready to play. So that's why this is this way. Again, welcome everybody. I'm going to be the MC for this. Jamie Howarth and John Chester are going to present to us about the Plangent process. And we're looking at a diagram of the process here, I believe. You can read their bios on our webpage in the meeting announcement. I'm not going to read that to you again, but I will say that I met John Chester the first time at an AES convention 3 years ago, I think, while I was talking with Bill Hanley about and learning more about his wonderful work at Woodstock. And I've since learned a lot about John's wonderful work at the Fillmore East and other places, and with Plangent as well. And when we wanted to do a meeting, I'd heard enough about this process to know that it seemed like a really fascinating thing, and that it would be good to learn more. And we're honored to have all of you with us. And I'm just going to throw it to Jamie now, and welcome and thank you for presenting to us. So Jamie Howarth.
Thank you. Thanks very much, guys. I appreciate it. And John, I'm sure I speak for John. I thank you all for letting us into your schedules to take a look at something that we've been doing for a while. I'm very excited about, and hope we can make it clear to you what it is that it does and how it works. As Bill had said, I can't. You're seeing a lot of things like as if I was drawing the screen, or transitions, animations, whatnot, the PowerPoint, simply because we went through quite a bit of aggravation last night trying to get the audio to be in stereo and everything else, and it turned out that we have that. So once I got it, I'm going to play with it. I would, as a veteran of a lot of AES PowerPoint things, I really hate when they finally get to the audio and it's like an hour into the damn discussion. So let me just give you something right off the bat. This here is the bias at approximately 120 kilohertz. This is from a Nagra recording that Betty Cantor did in probably in the mid 70s, and it sounds kind of like this. Let's see if that's loud enough.
Be louder.
I ask you guys to turn up your cells when this is going on. Again, this is a little bit chaotic. If I switch out of the screen, I'm going to lose the audio. All right, so there it is. Here it comes again. Now, what happened there was that John was describing last night, the little switch on a Nagra that puts it in fast forward actually works when it's in record. So somebody accidentally jostled that switch, and that's the result. Tracking the bias, which we can get into what that means, here's your result. So that's one. There's another one that's similar. This might be a little bit louder.
Say that when your ship comes in.
I guess belaboring the question as to how it is that you make the same mistake twice in the same show, but here's...
Save it when your ship comes in.
So that's basically what it does. Works with alacrity. Let me just make sure I know what I'm playing here. This was quite a surprise to everybody.
She cuts you once, she cuts you twice, still you believe. The wound is so fresh you can taste the blood, but you don't have strength to leave. You've been bought, you've been sold, you've been locked outside the door, but you stand there.
That's a ATR fighting with a piece of tape that probably should have been baked before it was put on the machine.
You've been bought, you've been sold, you've been locked outside the door, but you stand there.
You can see this here is obviously, this is the gyrations of the machine during that moment. And I'll get into what actually produces this signal in a second. But let's see, short fix. This short fix, long D. Wow, okay, I want to play the right one.
She cuts you once, she cuts you twice, still you believe. The wound is so fresh you can taste the blood, but you don't have strength to leave. You've been bought, you've been sold, you've been locked outside the door, but you stand there.
So what was originally
You've been bought.
the let's see if I can just get to this in a second here.
She cuts you once, to leave. You've been bought, you've been sold, you've been locked outside the door, but you stand there.
And that became this.
You've been bought, you've been sold, you've been locked outside the door, but you stand there.
So it works. And the question is how. And that's where this is a basic block diagram of how it operates. I think it would be fun, though, to describe to you guys how it was that I first came upon this. Like many ideas, this is not... I've heard about this idea from other people. In fact, I just ran across somebody who said that they put in some kind of a patent application sometime back for a variation of this back in the about like 10 years ago, 2010. We were already ahead of them, so that's the way it goes. But when I was a kid, I worked for a company called Audio Techniques in New York, which was the pretty much the one-stop shopping besides Gotham for audio equipment. They were an MCI dealer, for better or worse, but they had every toy you can imagine. We were in and out of studios a lot. At the time, one of the most complicated consoles before the SSL came along was the MCI 500 and 600. And Howie Schwartz, who was one of the founding members of SPARS and had a big jingle studio, and he hired me pretty much to show him how he hired me away from Ambrosius to show him how the consoles worked. And it was a great opportunity because I ended up assisting Roy Halley and a couple other real big names to show them how the damn thing worked. But one of the other things that Howie wanted to do is he wanted to prove that he was the smartest guy in New York, which was very, very competitive atmosphere, and everybody in New York at the time was using 456, and Howie wanted to prove that 250, which was his favorite tape, was a better piece of tape. So I was assigned, given an MCI 2-track and a very early Hewlett-Packard digital frequency oscillator that must have cost 50 grand, and a Genrad general radio spectrum analyzer that must have cost 50 grand. And why? So that we could prove that Howie was right about the tape. And actually, just being a naive young kid, I really kind of blew it by telling him that 468 was actually the best, but at what he was trying to do. But that's a whole other story. Anyway, the way we were trying to test these was to put down a 1K tone or a 10K tone coming off of the frequency generator, which on a spectrum analysis an FFT looked exactly like a single vertical spike, and then play it back off tape, and you see the machine drifting back and forth in sort of a pine tree shaped distribution of whether, you know, it was pretty good, and then the sways and back and forth, and it was basically a frequency representation of how much the machine was speeding up and slowing down. And as it happened, these were 30 IPS tapes, and I remember scrubbing one of them really slowly to try to find a particular point, and I hear, and it sounded like a bad Moog BCO filter. You know, it sounded really nasty, noisy, but obviously very, very pitched. Now, my background is in music. I kind of faked my way into the engineering side of it, because back then that was the only way that you could get a demo that sounded like you wanted it to, at least in the boonies where I was. And so I had a musical background, so I'm listening to this thing, and I got pretty good pitch and, absolute pitch, and I'm thinking to myself, wow, that's interesting. What the hell is that? And Tom Cahill, who used to be the chief of Atlantic Studios, and he was there. And I showed him what I was listening to, and he said, oh, that's the bias. Oh, all right, that's the bias. So basically what I was hearing when I was scrubbing the tape very, very slowly was the bias of the MCI, which was pretty damn high. If I remember correctly, the MCI is 226 kilohertz, which is way up there. And scrubbing it very slowly, could hear, a high-pitched whistle, and my first thought was, well, the MCI had a very complicated, basically it was a modem. It had a little bit of a photocell underneath the capstan and some other things, and the logic was very, very early and crude, but basically what it was it had a 19.2 square wave generator, and it compared that to what was coming off the capstan and blah, 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 and it slewed the machine back and forth. And so it had a rather complicated, finicky, difficult to set up servo system that worked really well when it was working. But I was like, why isn't this used as the servo source? And in the typical kind of folk art fashion that happens quite often in the business, well, it's not really recorded on the tape. I'm like, well, I just heard it. Well, no, it's, that's just, you just got lucky. It's not really there. And it bugged me. It bugged me for years. It was an idea. I thought, if you could resolve that, if you could make the machine act as if it was an FM receiver, or transmitter, and then receive that signal, that carrier signal, if you will, and then demodulate what the speed changes that were in it, the frequency changes in it, and make a map of that, or feed that to the servo so that you had a preview head perhaps. And many years went by. Dave Smith, late Dave Smith of A&R Recording and Hit Factory and Sony Music Studios, and he and I batted this around quite a bit. And, it was one of those things never got around to. When I left the job, and I had at ABC for quite a while, I left in 2000, and this was just really bothering me. And so I went ahead and I bugged everybody at the AES shows that I could get my hands on, the older guys, Dale Manquin and Greg Orton, and obviously John French, who was a great ally of our efforts at the early part of it, and talk to these guys all about what would you do if you had an opportunity to build a tape machine that you didn't have somebody at the conference room arguing with you about every damn cent you were paying, and what would you do now that 25 years later, because there really hadn't been a whole lot of progression in this. So the ATR 102, which a lot of us geezers think that's a modern machine, and when we press play on it, but it was actually designed, if I remember correctly, in 72 or 73. John could correct me on that, but it's definitely old. And other than the 810, 820 Studers, which are recapitulations of Studer designs that are really from pretty much the same era, there hadn't been any effort to make a playback system that was, other than the Aria, which I bought one, and we certainly used that as a benchmark for quality, and I hope we beat it. But the methodology for this is where this diagram will come in. And Dan, if anybody texts you that they're lost, just hit me up and I'll back up a step.
Yeah, no text so far.
All right, well, that's basically the history of it. Was this kid at Howie Schwartz recording, listening and hearing this mysterious whistle, and it turned out to be the bias remnant that was audible if you slow the tape down enough. And So that came as in all recordings, modern recordings from the 40s on. There is a bias oscillator that simultaneously with the audio is recorded by the recorder. Now, this is blasted onto the tape. This is I was reading Marvin Cameron's paper this morning, and it's a refresher, and it's 5 times hotter than the audio. And it typically is an oscillator that would range from 40 kilohertz, about the slowest I've seen, up into 432 kilohertz from ATR 102, which so far we haven't been able to locate. There's other ways to fix an ATR 102 with their servo bus that they make, but anyway. So the notion of the bias is, it's a long, complicated explanation, but the most fun story on it was that the Germans pre-World War II were trying to figure out how to time shift Hitler's speeches, and eventually start playing games and time shifting the Berlin Philharmonic, playing at 2 o'clock in the morning, and the GIs were like, how the hell are they doing that? Because the high fidelity, we didn't have anything like that. We didn't have anything at high fidelity. They did. And it was like, how are they getting the Berlin Philharmonic live at 2 a.m.? They're not. So Mullen and those guys knew something was up. And one of the stories, which probably has got some salience, is that there was a machine that they built that suddenly sounded wonderful, and they couldn't figure out why. Now, bias had been around for a while. You can DC bias something with a permanent magnet. Basically, the idea is to try to get the very, very narrow range that magnetic materials will actually be linear. You push the tape, and you push the tape, and you push the magnets, and and then you pull the magnets, north and south, pull them north, pull them south, push them north, pull them south. And they aren't really happy about doing so in a linear fashion.
Jamie?
Yes.
Luke suggests that this would be a good time to say what the bias function is.
Well, that's what I'm going at right now.
Okay.
The bias function is to, the reason that this was fascinating to these guys was they had one machine that sounded really, really good. And they couldn't figure out why. And it was a DC bias machine. It was just a permanent magnet, that was scraping along the tape ahead of the recorder. And basically the idea was that would offset the level of the recording, so there was in a more linear part of the magnetization. So that actually would, if you tried to hit it with a sine wave, it would give you back a sine wave instead of, overshooting, undershooting, being a square wave and distorted and terrible. So anyway, this machine sounded really good, and they went through it and fixed a few things, and it started sounding bad again. And one of the things they fixed was a cold solder joint that apparently was acting as a radio receiver, a diode receiver, like a crystal radio receiver. And it was picking up a local ship-to-shore transmitter that wasn't far from where they were working on this machine, and that was broadcasting itself into the head at tremendous level. They didn't hear somebody speaking, or they didn't hear any audio, but what did happen was essentially that higher frequency, 200 kilohertz injection of that RF caused what later became theorized in a lot of different ways. Mostly Marvin Cameron is probably the best on it, as to how it was linearizing the audio, so that the curve, the area of the curve where it would go from zero to saturation was really linear. You 1-for-1 function, or pretty close to 1-for-1, which it was not without the bias. And so basically what happens is the bias rides on the audio. The audio rides on, I misspoke. The audio rides on the bias, and there's a tremendous amount of swing in the amplitude of the bias. Again, it's 5 times hotter than the audio is. And essentially once that's gone past the head and the audio is fixed, the magnetic materials are no longer responding to that particular bit of audio. You now have a great low distortion recording. And what was thought to be the case was that was not persisting on the tape. You can read in the document, in the papers written on this, but it doesn't persist on the tape. And obviously it had. So what what we built, David Smith was helped with this, and some guys up in Canada that built a prototype on it, was essentially a really, really wideband preamp. The preamp is way, way wider than it needs to be. Obviously, you need 20 to 20K to get decent audio. This is out to 400 kilohertz, which is a real challenge as far as noise and RF pickup and everything else is concerned. And what that records is not only the audio and digitizes that, but also picks up the bias, filters it, shapes it a little bit, maybe shifts it in frequency so that it can be recorded at 192, 24, because obviously something's very high frequency, it has to be divided down, and that bias recording and the audio recording are made simultaneously. And you can't do it with two heads. And everybody says, why don't you do it with two heads with a preview head? And that's because you imagine you have a sticky edit that goes through the machine. It doesn't go through the machine. It doesn't stick at one place and then the playback happens later. It sticks everywhere at once, so the tape almost stops at once. And if you had a preview head, you would end up throwing that disruption into the audio with the delay that it would take to get the audio to back up enough to catch the preview head. Anyway, these two are recorded simultaneously. On stereo would be 3 tracks. And once that's done, there's a series of cleanup things that are quite honestly proprietary I don't want to get into. But the net result is that it is basically an FM receiver. And it looks at the frequency shifts that are happening in the bias. So these are higher frequency, lower frequency, higher frequency. Because what's the swing in the bias is identical to the swing that's in the music. If something goes up 1% at 100 kilohertz to 101,000, then the music has gone sharp by 1%. If it goes flat by the same amount, it goes 1% flat. So once that deduction is made as to what the actual swing of it is, what the actual demodulation, it ends up with effectively a pitch map or tempo map, a baseband that then can be used to take the audio and pitch shift it. There's an interpolator that does the obverse of whatever this says. If this went sharp, so we make the audio go flat, and vice versa. And the net result is the defluttered audio recording. And I should probably stop there for a second and ask if that was clear. Okay.
A question came up, does the process squash the dynamics?
No. Why? Why would it do that?
The Plangent process, I guess.
Why would it squash the dynamics? I mean, it's the audio. The idea of the audio being as absolutely transparent as possible. If you listen to the preamp as it was built by these guys and designed by Dave and then redesigned by John, the audio is fabulous, regardless of whether you do the Plangent aspect of it or not.
Right, and Plangent only affects the pitch.
Yeah, it does
not affect the dynamics in any way.
No.
Other than the fact that in removing the flutter, you may perceive more of the dynamics of the original recording because you can hear further into the mix. But that's done by making all of the individual components of the mix purer and closer to what went into the tape machine.
Yeah, that's exactly right. No, there's every effort is made to not do anything deleterious to the audio. And one of the things that I can't speak to, and as far as the pitch shifting is concerned, this is not Serato or TCEX or any other pitch shifter, auto tune or anything like that. This is basically, first of all, it's a priori. It's using something that the original recorder made that is quantifiable exactly. So there's no guesswork involved. There's a couple out there that try to tune everything to A440 and see if there's some variations within the musical material itself. And unfortunately, they suck out vibrato and have some other artifacts, and they can't work very fast. If they work fast enough, they're going to start taking the violins and turning them into a straight line. So we don't do that. We're using a signal that's known and separate and distinct from the actual audio, but that does have exactly the obverse of whatever the problems were as far as pitch goes and the speed and tempo in the audio.
Yeah. Another question came up from Robert Pettis, and Robert, I'm going to have you ask it rather than have me read this question here. Can you unmute yourself, please?
Yeah, can I be heard?
Yes, thank you.
Okay.
Go ahead.
I'm in possession of some early CD transfers from the very early Sun Masters, and there was an interference between the bias and the digitizer, the frame rate of the digitizer. I've had that, and it made a whistle on the CD, a very faint one, but I knew what it was because I've had some experience in that. And right in the middle of the recording, the whistle frequency changed quite a bit, meaning the bias frequency had changed. Now, that wouldn't have been heard in the original recording. It was only an artifact of the digital transfer. Wouldn't the bias frequency changing trip up your process?
Not at all. It's a reflection of an edit. This happens, for example, I'll give you an example of from Who's Next. Won't Get Fooled Again is a great, obviously iconic song, and it's 8 minutes and change long. And Glyn Johns actually apparently nailed it on one reel of tape. He did it in 3 sections. I pulled myself and my family aside if we happened to be left out of the line. That's one of the cuts. And then it actually goes through a lot of the long synthesizer section is another section of it. And then at the end where the scream happens after the drum fills and whatnot, and just before the scream, there's another cut there. And it's quite easy to see the shift in the bias of those edits. Another one that's a perfect example is if you remember the Country Girl, I Think You're Pretty from the end of Deja Vu, which is a three song trilogy, and those 3 are actually there's 5 cuts in that, but there's very clearly steps in those. And Won't Get Fooled Again starts at A440, and there's a lot of evidence that Townsend was using Kahn Strobe tuner, so he knew what A440 was. And by the time you're done the end of the record, it's flat. It's down about 437, 436 and change, which isn't a hell of a lot, but you wouldn't want your piano tuned that way. And the reason for that is that the machine's supply reel was emptying, and it was because allegedly constant speed, but of course that was at the mercy of the amount of weight that was on the supply side. As it got lighter and lighter, the machine ran faster and faster. So of course when you play it back now on a servo-driven 15 IPS dead nuts machine, you're going to hear the pitch actually drop. So couple thoughts on the particular tape. I'd love to see that, by the way, Robert, if you wouldn't mind posting a link to that Dropbox, because I think it would be fascinating. That tape actually is we've seen that tape. That's a 30 IPS quarter-inch copy made of the Sun Sessions at RCA in 1956 when they bought the catalog from Sam Phillips. And it has 68 kilohertz bias on it like gangbusters. I mean, it is as loud, if not louder, than the audio. And the reason that that's remarkable is because, there's no head in the world that doesn't have some kind of drop off from 20K to 40K to 60K to 100K or whatever.
But that bias is so hot, it just comes out anyway.
It's unbelievable. And to have that beat against the 44.1 clock is not really that not surprising to me. If I were cutting that, if I were to be the producer, now that I know, producing an LP on that, you would hope that they would filter that out before it got to the lathe. Great story Dave Glasser told us about the early DSD SACD, where they tested it at Airshow Studios, and his Bryston amps thermaled out because of the amount of 70 kilohertz noise that was there because of the noise shaping of the. It's the same kind of thing would happen here. So that it would BFO, if you will, beat frequency oscillate back into the audio is it's pretty interesting. Probably would be trackable. You'd need to know what the original bias frequency was, though, which is tough to deduce, but you probably could figure it out. So that's why that phenomenon exists on the CD that you've got. When they played it back, it was so freaking hot that it got past the A to D, got past the aliasing filter, and it folded over.
So, how you say you wanted to see that example? How would I get it to you? I'm not going to be able to generate it during the time of this call.
Well, there's a Dropbox that I put up. There's Plangent public, which should be in the, which will be included in the chat, that has this PowerPoint demonstration, and you just want to lob it up there. If anybody has anything they want to lob up there to take a look at it, certainly we always are happy to look at anything, and something along those lines would be fascinating enough to take a look at. It happens that we did some tests at Sony Legacy some years back, and one of the pieces that Mark Wilder happened to have in his room that day was that tape. So we digitized That's All Right Mama, and it comes off pretty well. Comes off cool. One of the things that I think would be worthwhile to interject right here is that most of us who are engineers, when we listen, a lot of times we're listening for quarter dB at 10K, or what's a distortion, or is there something wrong, or has there been some artifacts, digital artifacts, and so on and so forth. And again, the interpolation, the interpolation's non-real time. It's typically 128 to 256 times oversample to 192. So I don't know, it's like 12.8 megahertz or 26. So it's pretty fucking dense how much the oversampling is, in order to be able to make sure that the pitch shifting is really smooth and not full of any artifacts. So the fidelity. Go ahead.
I see an interesting question from Jerry Jensen here.
Yeah.
Which I can answer, and he's wondering how we choose the center frequency for the demodulator. And yes, of course, the demodulator does go down to DC, and at the very least, the center frequency has to be chosen so that at some point in the playback, the center frequency is equal to the bias. Now, ideally, we would look at the range of bias frequencies that we encounter from the tape in advance of actually doing the transfer, and choose a point somewhere in between the highest and lowest bias frequencies that we see.
Yeah, and then I go back and make them all A440. So really, it's the number's close. The number on, if I remember correctly, the number on one kit pulled again was like, it was really right up against Nyquist. It was 94.2 or something like that, and it went from 94 to 95 and down to like 93.5 or something. And basically I just said, okay, the beginning of the record, what's it measure at the beginning of the record? And that's what I put in as the seed number, and then measured it after the fact and said, all right, that's a couple of cents off, and we have a parameter in the software that'll do a global shift in order to be able to get something in pitch, and that's, essentially what John is saying is, I most of the time, you could look at the middle of the tape and go from there. We did that for a while, but now I'm just kind of like, where are we starting at? Where's it start at? Because I found that people were just distracted and surprised by hearing something that had a different, when I was playing it before and afters. If there was if I did measure the middle of it, and the beginning of ours was considerably flatter than the original, that may be correct, but it would throw people off. So at least for demonstration purposes, I got in the habit of using the very beginning, so that when I heard it come back, I didn't hear a pitch shift that was an erroneous, pitch shift. And of course, after the fact, once it's all done, then I'll go back and tune it. So that.
Before we leave Robert's question completely behind, I wanted to clarify. He's talking about some commercially released CDs that have a problem that the CD production process interacted with the bias to create a third thing. If you were going to fix that, you would not use that CD. You would go back to the original tapes. Is that correct, to get rid of that wow, the wow and flutter from the bias varying? Are we frozen now?
Well, I don't know. I thought Jamie was going to answer that one.
I think we lost Jamie.
I think we lost him altogether here, yeah.
Yeah, anyway, well, I'll answer that question.
Okay.
I bet that it could be fixed to a certain extent based on the signal that's in the CD, but obviously it would be a whole lot better to go back to the original tape and use that, and also not have the whistle in the transfer that you had to get rid of.
Yeah. Yeah. Okay. And
Well-
then Alex asked a question. Back in the day, did artists compensate for the tape medium's limitation to where this process could negate that and create undesirable artifacts?
Is that specifically referring to pitch variations, or is it referring to taking out other effects?
Alex, you want to elaborate? How would you compensate for the tape medium's limitations, I guess would be the first thing. And then would you lose those compensations?
A lot of people, for example, liked to overdrive tape because they liked what that sounded like. And in that case, the output of the tape recorder certainly didn't sound like the input. But we're not going to remove that distortion. We're going to remove things that affect the pitch. And I won't say that I've never heard a case where I thought that the original was better than the defluttered one, but usually I like the defluttered one a lot better.
Okay. I think we have lost Jamie altogether. I'm monitoring the waiting room. And he's not
Can you guys hear me yet?
Yeah.
Oh, you're on an iPhone.
Right.
Okay.
Yeah, I'm on my phone. I had a panic crash. So I've never seen, I haven't seen that before in years, but the machine absolutely just died. So go ahead and if you continue asking questions, and John seemed to be fielding questions quite well, and I'll get myself back on here. Okay. So, all right. Now the machine came back, but I'm obviously gonna have to go through all the machinations to get it to work right again. So.
All right. Any other questions, folks?
I have a question.
Greg.
John, could you maybe talk a little bit about the importance of the two tape machines as a part of this process? I think I missed that.
Two tape machines?
Well, in the diagram that was posted, there was.
Oh, you mean the fact that we record a separate signal for the bias?
Yeah, could you talk about that a little bit more and try to help us?
Because, I mean, the two tape machines shown in the diagram are simply intended to represent the recorder and the playback machine.
Oh, okay. So that's
so the recorder is the recorder used by the creator of the tape, and the machine on the right is the one we use to make the transfer. And when we make the transfer, then we have a digital setup that records both the stereo audio or the multi-track audio, if it's a multi-track tape, plus an additional track which contains the bias signal.
I see. So you use your digital process to then alter the analog process the second time.
Correct. It is certainly not a real-time fix. When I do the transfer, I hear all of the wow and flutter that's on the recording, and then I ship the files off to Jamie, and Jamie runs them through the digital part of the process, and they come out fixed.
Thank you so much. That helps clarify it for me.
Okay.
Okay, I need to be reestablished as the as a host on this so I can get back in.
I think if you just need to share a screen, but
well, it won't. Host disabled participant screen sharing. So
Greg,
I've
that's
made
probably
you a co-host.
All right, original sound is on. Where all right.
Hey,
I got to get the PowerPoint back.
I just wanted to address what we were talking about with Robert's question with the sun stuff, and I guess also ask John and Jamie a bit more about that. If it wasn't clear, I think, Jamie, what you were saying is that it's not that the bias on the recording machine changed, it's that the speed on the recording machine changed. So what were the bias that was coming across in playback changes in pitch, and then that's why there was that issue.
Well, let's take the example. Many early tape machines, it's fairly well known, changed in speed from the beginning of the reel to the end of the reel. So if you have multiple takes and you edit them together and you splice a piece from the end of the reel next to a piece from the front of the reel, then the pitch is going to change a little bit. And the change in the bias frequency will show that pitch change. And after we get done with it, that pitch change doesn't exist anymore. Does that answer your question of where that pitch change could come from and why the bias frequency changed?
Well, I understand that, and I wanted to make sure Robert understood that. But then also, I think his question was, or his assumption was, is that the bias oscillator on the machine was changing when it was recording, and the question was, are you guys aware of that ever happening, where the bias isn't hardcore fixed frequency, fixed generation during recording?
We have never seen a case where there was an abrupt jump in the bias frequency, which was caused by the bias oscillator. The one case we know about is the 3M machines typically had a thermal drift problem in the bias oscillator. And so when you put them into record, for the first couple of minutes, the frequency of the bias slowly drifts. And we have learned to compensate for that. But a rapid jump in the bias frequency, no, never seen that.
Yeah.
If there's a rapid jump, it's always the result of a splice.
Yeah. There's one in it's a long guitar solo in a song called Words. There's a Neil Young, I think it's on after Gold Rush, and it's just massively flatter right in the middle of the solo, and that's again because they had pulled up from, they discarded 10 minutes worth of tape and the machine was running at a different speed. The bias oscillator was, they typically are quite stable, with the exception of that crazy 3M, which for the first 8 or 10 seconds might act up. But it settles down. The original tape players in the States, recorders in the States, were based on the Armstrong circuitry for the ship for the walkie-talkies in the Pacific theater. So their oscillators are good. Those are signal core oscillators. They tend to be pretty stable. So
they're more stable than they needed to be, which is really good for us.
Yeah, they're way more stable than the transport too. That's the other thing is it they're low jitter. The later machines, the ones that are quartz crystal, I mean, it's insane how precise that.
Well, that's not so surprising, but the surprise is that the LC oscillators are way more than good enough to do what we're doing.
That's true, and they're way better than the machine is.
All right. Anyway, we should, if you want to play other samples, we should do that.
Yeah, we should.
It's getting to be time to move on to the rest of this.
All right. Let me go back to where I was before I got so rudely interrupted. Let me just check and see that. Can you guys hear this? Is that back in stereo and whatnot?
Yes.
Okay.
Yes.
All right. Very quickly is one where I was going. The machine blew up on me. Is that we as engineers are accustomed to talking about the technical aspects of it and 2 dB at 10K or 10th of a dB at 10K or how much third harmonic distortion there is. And I had a really interesting experience when first showing us at the AES many years ago in 2004. And I happened to run into Jim Keltner, who's a session drummer who worked on a million things, a lot of Steely Dan, and you can imagine. And I happened to know him through another context a little bit, and so I dragged him over to the booth, and he said, "What do you got to listen to?" And I had Simon and Garfunkel's "America," which was Hal Blaine, and he listened to it, and he stopped me. He says, "Why does Hal swing so much harder in yours than he does in the original?" And I was like, no, that's interesting. I don't know, because I'm a musician, I'm a pitch guy, but he's a drummer, and he's one of the best drummers in the world. So I played it again, and sure enough, he's right. I'll come to look for America. I mean, he's like, he's playing in 12/8. He's banging the shit out of a ride cymbal all the way through there, and yeah, he is more steady. Does seem more steady, and I'd not noticed that before. Then I went on. A friend of his apparently was Corky Lang, who was the drummer in Mountain. If anybody remembers Mississippi Queen, I'm sure many of us do. And he says, "Oh, that's interesting. Corky was an underrated drummer. I don't understand why he wasn't as big as Mitch Mitchell and the other guys. But you have that?" I said, "Yes." I played Mississippi Queen. He almost jumped out of the chair right after the first couple of seconds of it because it was so much more steady. And he says to me, "Damn!" In the original, he sounds loaded. Apparently they partied together quite a bit, so they knew what that was. He said, "In the original, he sounds loaded. In your version, it sounds like Corky." And so I went back and started thinking about this. More recently, I've begun thinking about this from the performance aspects of it, as well as the electronics. Obviously, the electronics are real, real good. But one of the things that's interesting is how much harder something might rock. And I don't know that you'll be able to hear a whole lot of fidelity difference in this, but if you listen to the drumming on it, the two drummers, maybe you get the idea. Let me get this going here. And the processed version of it. So it's not necessarily always a matter of the fidelity. There's a situation, again, even on the Zoom, you may be able to hear this, but the original is a little looser. That's one more time we're here. And that is only a matter of about 0.1% of wow. What's going on there, though, is that the wow is not sinusoidal. The machine's actually stepping up and down a little bit because there's some kind of bearing problem or some other problem that's causing it to drag and then speed up and drag and speed up. That's changing the tempo. And it was enough for Keltner to pick up on it. And it's something that after a while I realized has become much more important in my mind because the performances then suddenly become what they originally were before the introduction of the abstraction layer of the speed problems caused by the machine. I'm going to get out of this in a second, but this is one of the better ones also.
The strikers are having their big Christmas ball.
And that's a 42 kilohertz bias on a Webster wire machine.
Where the strikers are having their big Christmas ball.
So, at some point the fidelity obviously is really important. The dropping in IM is quite a bit. There's here's what that looks like, just so you get an idea. This is a standard straight ahead 1200 hertz tone right out of the signal generator in RX. And here's what it would look like with 3% flutter. And the flutter rates are 30 hertz, 120 hertz, and 2.5 kilohertz. And as you see, there's a whole bunch of extra information in there. If that was a A440 flute, you'd have 470 and 410. Some in different products would be in there as well. That's pure intermodulation distortion. And here is what it would look like at, what is it? Come on, switch, 110. That's one, no, that's wrong. It's the wrong picture. All right, anyway, I have to repair that. Anyway, that's what 0.3% looks like. And so all of that extra spread spectrum, all that extra information that isn't supposed to be in there, that's blurring everything, is part of why the fidelity's better. But what's interesting is that what had this kind of smear in here, and what you get back is that. And you can see that in the Guthrie. Here's the original swing of that Webcore machine, and there it is after it's been dewowed. It's now standing straight up, not moving. So that's it for me. Unless whether you got more questions, and can I help explain further?
Jamie, I have a comment. I think I'm hearing your iPhone broadcasting or
Yeah,
picking
you
up the
probably
sound.
am, and I was
I've
afraid
got
to
it
turn.
muted, but go ahead and turn it off.
Okay. I'm afraid if I do that, I'll lose the meeting, but I'll turn off the phone.
Well, just turn the volume down.
It's all the way down. Thanks, guys.
Of the speaker? Okay, good.
I do this for a living.
Thank you.
I'll put it outside. Just threw it on the floor. So anyway, anything else?
Yeah, any other questions for Jamie before we move to John? How often did you see tempo issues is a question.
Always. Not to be a wise guy, but they are always. It's interesting once you know to listen for it. The amount of, again, 1/10% of a step wow, which is what was on that Mississippi Queen, by the way. And if you look at that, that's 4.8 ticks at 480 parts per cue, quarter note MIDI. And you can certainly hear 4 ticks. 960, that would be two ticks. So the degree of precision that was demanded by, say, Steely Dan, those guys, and Roger and whatnot, when they bought what essentially became Logic as a 960 parts per quarter note divisions in the MIDI, that was not enough at 480, and that's about, the machine was slightly worse than MIDI. It's just nobody ever thought of it as being one of the things that could happen. Won't get fooled again, too. I mean, it's interesting. Meet the new boss, saying is, shouldn't reveal too much, but I think you might be able to hear that one of these days pretty soon. But meet the new boss, same as the old boss. That moment that happens is actually slow in the one that we've heard for 1,000 years. And when it's on the right tempo, even ever slightly brighter in tempo, the energy's different. It's much more exuberant, much more in your face, and not as sardonic. It reads differently, So yeah, here see tempo problems quite a bit. You see pitch problems quite a bit. Obviously, sometimes they're very, very, very subtle. None of these recordings are supposedly bad enough that you should be able to even hear a pitch change. To hear a wow in Flutter, that's way below the threshold of audibility. This proves that actually the threshold of audibility was considerably higher than what we thought. One of the things that Keltner did say was that he was in these sessions and he would be looking over his shoulder at the other musicians in the room when they come in after a take. They'd be looking over the producer's shoulder saying, geez, the kind of eyebrows up, were we really jiving ourselves that we weren't as tight as we thought? In the cans, we thought we had a great groove and it was really cooking, really smooth, really slamming. And then we go in the control room and it's like, it's a little vague, and he said when this is the quote, he said, when the digital came in, my cymbals sounded like trash cans, and I hated that for a while. It got better, but that problem went away. That tempo problem, what they heard when they went back in the control room was what they had actually played. It was comforting because it was the first time that they actually knew that they weren't that they didn't have confirmation bias while they were playing, that when they went in the control room wasn't there anymore, and that they were actually looser than they thought. It was a machine. So, does that answer the question?
Yes, thanks.
Yep. Okay.
There's been a few other questions. John, are you going to talk about the reproduction head that you use?
I am. That will definitely be part of the later presentation.
Okay, so the next question is, how effective is this on spoken word recordings?
It's effective. It's not as easy to hear wow and Flutter on a spoken word as it is normally, as long as you're listening for wow and Flutter. If you're listening for the veracity, the there-ness, there's some Sinatra stuff. Again, this is not spoken word, but this is one of the best examples I can come up with on it, is that there's more there. It's more realistic. We're not used to hearing things destabilized. So again, that abstraction on a spoken word thing. One of the things that's interesting is you hear more back wall. You'll hear more more room resonance, more room decay. Nobody's really sure why that is. I talked to J.J. Johnston, who's obviously the top guy on this kind of psychoacoustic stuff, and I mentioned that to him, that in the if there's wow and some flutter, that it seems as if the reverbs are corrupted somehow, that the reverb isn't as comprehensible, And he says, yeah,
and the other thing we found was that if you had a badly wowed recording that had a lot of room reverb in it, and the room reverb sounded really lousy, that once you defluttered it, the room reverb, although it was still there, sounded like a real room and became much less offensive.
Yep. Yeah. And there's obviously this is my thing. So of course I've got to, I extrapolate a lot of different places. But one of the things that's interesting also is that here's a mind teaser for you. I remember going into the AES and George Massenberg goes up to the late Mike Spitz, God rest, and Mike is showing an ATR and George goes up and pushes the head block on the ATR, which is soft enough that you can hear its swish. And George was like, the azimuth is off. And actually, no, that's not what's going on. What's going on there is the pitch shift. Pitch shift at 10 kilohertz when it bounces off the wall and it's 6 milliseconds to the wall and 6 milliseconds back to you. That's a long time. And that's going to
the point is it makes a really narrow comb filter.
Yeah, it makes a comb filter, it makes a flange. Okay, so the flanging that's happening off of the walls and the acoustics in the space that you're listening to the music in is something else that you're constantly trying to decode. And also, as John mentioned, in a recording where there's a lot of room reverb in there, and the brain is trying to rationalize that. And if it's moving around, that doesn't exist in nature. Phantom center doesn't exist in nature. Where in the hell in nature are two sound sources that are operating at the same level in phase? It doesn't exist. So now put that into a situation where not only are we trying to comprehend the various bounces and reflections that are coming off the wall, but we now time-based shift that so that what was happening to the direct signal is flanged against what was played a half a second ago or 30 milliseconds ago or 10 milliseconds ago. It's really, really destabilizing. So yeah, that's on spoken word. You tend to hear the room, and you hear a more veracity in the speaker and the announcer or lecturer. Just more there. It's less abstracted.
Okay, a couple more questions before we move on. Robert, who brought up the Sun recordings earlier, said that it was Mystery Train from Elvis. There's a huge spike at 16.292 kilohertz. When he was younger, that bothered him, but now that he's old, he can't hear it. I know the feeling there. He had to slow it to half speed, and he's processing it for upload. And
thank you. 16 plus 44 is about, 60? Which is, remember exactly what the frequency was of that recording, but it was in that neighborhood.
It's in that ballpark, yeah.
Yeah, so you would get a fold over 44.1 at that frequency pretty easily.
Okay. And just a comment, he's processing it for upload, and that he's uploading it to the Dropbox that you gave us last night that I sent out to everybody.
Terrific.
That had those two the PowerPoint versions in it. Is that correct?
Yeah.
That's where you want it. Okay. And then the last question for now is, does this work with cassette originals?
Oh, well, yeah. It's some. John loves cassettes.
Can I
go ahead?
A quick answer to that question?
Yeah, well, if you can come up with a quick answer, sure.
There are many cassettes that we have not yet managed to recover bias from, although there are some. But if there are any other signals on the recording that came from other sources, and we've seen things like clock signals from various digital musical instruments, video sync, anything of that sort that was a stable signal to begin with, we can use that signal to deflutter it. So cassettes, the simple answer is maybe.
It's interesting. The dictation cassettes. I got a bunch of stuff once from a historical project done up in Maine of old folks. That were speaking into a Sony dictation machine that was at 42 kilohertz, and it was obviously battery powered. It was jumping around all over the place. And they asked if I could do anything with it, and sure enough, yeah, there's the 42 kilohertz. That was about the highest that I thought you could see off a cassette, because the cassette's really, really slow. And 15 IPS, 30 IPS, you can get quite a bit. 15, it's pretty much. 7.5, it starts to get tougher by the time down to an H and 7/8. We didn't even know if it was recorded, but just got a couple of Grateful Dead tapes that were recorded on metal. And I think are those metal, John?
Those are metal tapes, and they had 80 kilohertz on it.
80 kilohertz on it. Yeah, I'm tracking 80 kilohertz now. That's the signal to noise ratio of it is about 2 dB. But that's not the end of the world if I can find a way to carve it out well enough that I need about 6-8 dB to really do a credible job with a crude DWOW that'll make the thing sound like. One other one that came through, which was interesting, that amplified John's point. There was a Whitney Houston Radio City Music Hall show that was included in the Bodyguard soundtrack, and they'd lost one of the DATs. And so they had a cassette of the DAT, and the cassette was made simultaneously in the truck probably next to the DAT machine, probably next to a Studer multitrack or something, because there was very clearly switching power supply noise that was modulated, that was wowing. It looks like a hexagram. It looks like the sonogram of it looks like like 10 airplanes doing contrails, and they are swinging up and down, and dug one of those guys out and used it, and it not only fixed it, but Wilder said it sounded about the same as the DAT. It was a Nakamichi recording. It was a well-made recording, and it was quite surprising how much less like cassette it sounded like as when the WoW and Flutter was out of it. And that was the only thing that was changed. Obviously, it's a hot rod machine. John's got a Nakamichi from hell. But
well, we've bypassed a lot of the Nakamichi electronics, which were good, but not as good as can be done today.
Yeah, that's kind of our thing, is if you can beat it, we do. So it's very rare cases. One of the ones that's fun is a bunch of Springsteen live stuff that the harmonizer actually sings. And I was talking to Richie Factor about this at the AES, asking him, it's like, did you? And they, we had an LC tuned circuit. It was like 18 kilohertz. We didn't really care what it was. It was 18200. It was in there someplace. We just didn't even bother to make it very precise. And it's it's in the cassettes, and it's eminently trackable. So you never know.
Right. Okay. Well,
for this segment, is there ever been a case of detail that you cannot hear in the original tape playback, but you hear it now after your processing?
Mm-hmm.
Yes.
Yeah. One of them, I don't have it here, but I did the association, first two association records. I've been dawdling on the third one for a couple of years now, but the first two, including Along Comes Mary, which, just for the hell of it, that's this one here. And, the DWOW version of it isn't going to sound a hell of a lot different to you guys, but the synthesizer is steady. Okay, so anyway, I've got this record, and cherish is on that record. The cherish is a word I use to describe, et cetera, et cetera. And at the end of it, I'm working on it, and I hear, and I do doing, doing, doing. And I'm like, what the hell's that? It's in the right channel. It's part of the sweetening track. The tracking is left. The basics are left. A bunch of vocal overdubs and bounces and stuff in the center. And then on the right is like, whatever sweetening they wanted to add. Chimes in that case. There's a chime, an orchestra bells throughout the record. And then this thing at the end is, and I do doing, doing. And I was like, what the hell is that? And did a better DWOW on it and better deflutter on it. Got better and better. I was just tuning the thing up and making sure that it was getting the most performance out of it. And it emerged as a koto, which is something that they used on their second album a lot. They used a lot of Japanese instruments. Angular banjos sound good to me. That's a kitaro. So that little doing was one of the guys had come back from Japan and had one of those things in the studio, so they tuned it to one note and played it. And I'd known that record for, I don't know, since I was 15, 12, 13, I forget. It came out in 65. And that was probably the most revelatory. And it also taught something, which is that a lot of times the arrangers, they want to hear everything that they paid for on the record. That koto was on there, and it was just a little bit undermixed, and it was getting mixed. It was getting mishmashed around with a bunch of other stuff that was around it. But fixing that 2-track and making it really, really stable, and all of a sudden that little transient pitched instrument came to the foreground, and that was quite surprising. So yeah, all the time we hear surprises quite frequently. Yeah, and that's one of the joys of it. It's really cool. It's like, wow, I didn't know that was there, and I've been listening to that since start. So yeah,
cool. And Jamie, on this slide right here, there's 3 audio samples. Can you identify what each one is?
John can do more on this.
But when people go to play that slide back, what are those 3 samples?
All right, just so the legend here says, for the most part, the ones that have sound samples left, center, and right. And if you open it in the in this mode, this layout mode, you'll see my notes at the bottom of it that say what they are.
Okay.
All right. Typically, the unprocessed is on the left. There'd be a Plangent DWOWs in the center, and then there's an area that John can go into because it's really more his thing. Where, but it just as a layperson person, as a nutshell, it drives me nuts how many plugins there are that emulate an ATR 102 or a Studer. So you can take your digital signal and fuck it up with tape compression and everything else to make it sound warm and vintage and whatnot. And of course, we're driving ourselves nuts trying to go in the opposite direction. And so we're an unplug-in, if you will. I joked for a while that there would be a Plangent wower machine. As an April Fool's joke I put up once. But one thing that is real is that the machines cannot possibly pass a square wave. You put a square wave in the front of a tape recorder, and what comes out is a pretzel. And John developed this, which is basically an unplug-in. It's the instead of emulating one of these machines with the plug-in, the DSP actually reverses a convolution of the machine. We measure the machine's throughput, and then in DSP undo it, and that's beyond.
And there were machines that had analog phase compensation, and those were sort of effective at mid and high frequencies. It was virtually impossible to correct the low frequency phase error in analog, but it can be done in digital.
Yep, that's one of the reasons the ATR 102 sounds as good as it does, is that it was one of the first machines to actually attempt to phase linearize the throughput of the machine.
And it's right. What they did in the ATR is not a perfect match, but it pushes the phase in the right direction. It's better than if they hadn't done it.
Yeah, this is why it's more realistic. Again, anything that causes an abstraction layer that the ear can pick up on, which is not just 20 to 20K flat. It's it's a whole. As we get better and better at playing back music over the last 50, 70 years, is starting to really get into some areas that were unthought of before, which is that you can have flat amplitude and you can have something that has phase kinks in it per frequency, and they're going to sound very different. They're not going to.
Anyway, what this particular picture illustrates is that the way I devised to measure this is you make a test signal that consists of a fundamental and third harmonic, and the original test signal looks like the upper left. And as there's phase shift between those frequencies, it gets distorted as shown on the upper right. And then if you apply the right phase compensation, it comes back to looking like the one in the bottom center. Now that one has some amplitude error. You'll see that the two harmonics are no longer at the same amplitude, but you can differentiate the amplitude error from the phase error and get the phase error to zero out.
Man, it sounds good. It really does.
So I don't know that we have time to say a great deal more about that at the moment, but this is a separate correction that doesn't use the bias. It just means that we have to know from having measured it what the phase response of various historical recorders was.
And if anybody I'll play 10 seconds of a Plangent version and a Plangent version that has that compensation on it. And again, listen to the can sound, the rim shot sound of the tom-toms. You'll see it in. And this is with that compensation on it. So that's that. Let me give him that one more time real quick. It's worth the 10 seconds. And this is going to be a lot crisper, and they're more of the can sound in the toms. And those are both dead ass flat. There's no frequency response change in either of them. That's flat as a pancake. The only thing that's changed was what John was describing here, where the machine was linearized.
Again, and people can download this PowerPoint and listen to it on your own speakers without the Zoom processing.
That's right.
So, and Bob Smith points out that you can actually hear a difference over Zoom.
Good.
Great.
That's good to hear. You know, that's what we hope for. We hope that you can hear the difference on Spotify or MP3. I constantly giving MP3s to people before and after, and you know, I do it at 320 because I am like that. But they do survive the compression. This is in fact, the compression works a little bit better because there isn't as much sliding around of the filters all over the place trying to chase the original. It's more stable. So,
cool. Is there a list of all the recordings that you have processed?
Yeah. Actually, suddenly there is. Some character, God bless him, on the Hoffman site, and I don't know if Luke was behind this, but Luke certainly corrected him on a few of them because that's Luke. Came up with a very comprehensive list of all the of most of the music and most of the film that we worked on, and I can make a text file of that and throw that up too if anybody's interested.
Cool. Yeah, definitely. But Luke doesn't know what you're talking about.
No, he doesn't.
No. Do you have a link to that Hoffman thing?
I'm being facetious if you can't tell.
Yeah, I thought you might be. Hey, did you fill out your equipment profile yet, Luke? I mean, seriously, you know?
Oh, dear.
I know. Oh, DR. Yeah, got it. Okay. Those are inside Hoffman forum jokes, by the way, guys. So thank you for indulging us for a moment. John?
Okay. Over to me.
So, Jamie, you want to quit sharing here?
Yep. And let's see. All right.
And we'll spotlight John, Gary.
Hi there.
Hey. Hi.
So, we're going to start out just for fun with this. Here's a list of tape recorder bias frequencies, or at least a partial list. Gives you some idea of what we have to deal with. And this will be a little bit important to some of the following discussion. If you get all the way to the bottom and you see a Ewer report, it's because once upon a time, we did actually recover bias from a 3 3/4 IPS recording made on a Ewer.
Yeah.
It was actually closer to 57 kilohertz than 67 kilohertz, but we got bias off it.
Bill Evans, secret session, sounded wonderful.
All right. So for reference, because so much of what is going to be in the following discussion depends on various references from books that refer to what's on the tape by wavelength rather than frequency. Here's a handy table that shows you what the wavelength versus frequency is. Notice that we start on the left with hertz and inches. The middle column is hertz and mils, and then we have kilohertz and microinches. So when you're thinking about what kind of head you need to have to do this, I guess I got to jump ahead to this. When the wavelength on the tape gets shorter and shorter, it eventually gets to the point where you have one complete cycle of flux across the gap. And at that point, you have no output from the head because the average flux across the gap is 0. And that's what this diagram shows. So this is the output at low frequencies, and it gradually rolls off and eventually reaches a null, and then it comes back again, because at the point where you have 1.5 cycles across the gap, you've got output again. The dotted curve shows what happened. Well, the solid curve is calculated based on the physically measured gap size, but it turns out that that's not exactly what happens magnetically. And there's a lot of reasons for that, which I won't go into in depth at this point. But the average offset is about 14%. The gap appears to be larger than it is when you measure it physically, and that's what the dotted line shows. The other interesting thing about this is that it shows you that if we have a bias frequency that's higher than this null, that we've actually got some chance of recovering it at this point. There's some loss, but 10 dB is sometimes tolerable. And then we get to talk about other losses that occur. And this, you can ignore the straight line, which simply shows you that the output of a head changes with tape speed. But the other three show 3 of the predominant losses in the reproduction process. The one, number 4 at the top, is gap loss, which is the one we saw in the preceding slide. Then there's a loss due to the depth of the tape, or the depth of the oxide layer on the tape. There's nothing we can do about that. And that has to be compensated for in the record and playback EQ. And then there's spacing loss, and that refers to how far the tape is away from the gap. And although this actually takes a very small spacing to give you a great deal of loss. This is 6 dB down, and that's at 1/10 of a wavelength. And at 1 wavelength away from the head, it's down 54.6 dB. So the lesson from that is you better keep the tape against the gap. That includes things like making sure the surface of the tape is smooth, making sure that the head is properly lapped and doesn't have a flat spot on it, and having decent tape guidance. So now we'll show you the Plangent equipment. This is the front of the Plangent box. And that's the guts. And the boards on the left, well, should go a little further and then back up, because what's in, one of the problems is that in a typical tape machine, the head is connected to a fairly long cable that runs down to the electronics. And the head resonance in parallel with that cable is typically somewhere around 25 or 30 kilohertz. And therefore, the response falls off fairly steeply above that point. So one of the challenges was you got to have the resonance up above the point of the highest bias frequency you want to recover. The only way to do that is to have an amplifier that sits right behind the head so that we don't have any cable capacitance. It's also important to choose the correct inductance for the head, because if you have a head that's like the old ones, that's 400 or 500 millihenries in the head, then the self-resonance of that head, that is the resonance with just its internal capacitance, is probably only going to be 40 or 50 kilohertz. So we have to use heads with lower inductance than that. And then we have to have a head with a reasonably narrow gap. So the ordinary playback head we use for like 15 EPS tapes, we have a 50 microinch gap, which gives us a gap loss null that's somewhere just above 240 kilohertz. Makes it fairly easy to recover anything below 200 kilohertz, and still possible to recover things that are up to 240 kilohertz, although there's some loss involved in doing that. We'd love to have a better head, but unfortunately, people that can make innovative heads are a bit thin on the ground at this point. So what you see here is the signal from the head amplifier comes into the connector on the left front there. That's a balanced connection, because one of the problems with a lot of modern tape machines is they have a lot of digital stuff in them. And in the case of Studers, switching power supplies. So there's a lot of digital garbage floating around a modern tape machine. And if you have an unbalanced connection from something that's grounded to the head block to something that's grounded to the earth ground at the rear of the machine, you've got a lot of high frequency garbage on it. So we have to be able to deal with that problem. Then this board has analog EQ for 2 channels, and there are 2 of them, so we have 4 channels altogether. The board over here is the thing that down converts the bias signal to a lower frequency, because when we first started doing this, the best we could do was 192K sample rate. And there are some cases with bias below about 90 kilohertz where we could record the bias directly, but the vast majority of cases, even with machines that were nominal 100 kilohertz bias, that doesn't work with 192K sample rate. So the bias has to be down converted to a lower frequency. So the board on the right contains a precision digitally controlled oscillator and a mixer and a bunch of filters that act just like a heterodyne radio receiver and down convert a filtered bias signal to either 24 or 48 kilohertz. We typically use 24 these days. So this is our converter rack. The ones at the bottom are benchmark converters, which is what I started out with 15 years ago. They're not bad, but we like the Mitex better. And the other reason we like the Mitex is because these can operate at 384K sample rate. And although we're going to show you the old method of doing a transfer tonight, if we can do the transfer at 384K, we can dispense with the need to down convert the bias for many of the cases we have to deal with. We can get bias up to about 160 kilohertz directly on a 384K recording. It means we can just do a stereo recording, capture bias and audio on the same recording and not have to do the separate bias track.
John, There was a question about the different bias frequencies from each tape machine model.
Right.
Is there a reason why they were different? Is some better for some reason than others?
Yes, designers of tape machines.
Yes.
They made different choices. Well, originally it started out low because it was easier to generate low frequencies. And the other reason is that it's easier to get enough current through the erase head at low frequencies. And in the early days, the erase head ran at the same frequency as the bias. Eventually, there came to be machines that ran the erase head at a lower frequency than the bias. As you raise the bias frequency, well, let me back up a little bit. If you had perfectly bulk erased tape, it's as quiet as you can get. It's actually quieter than any recording that's made with bias. The bias generates a certain amount of noise. It turns out that that noise within limits is proportional to the bias frequency. And the higher the bias frequency gets, the lower the noise gets. So once you discover this and you discover that you have more noise in your old Ampex with 100 kilohertz bias than you like, then you think, well, I'll make the bias a higher frequency. So we go up to machines that have bias in the 200 kilohertz range. And eventually when they got to the ATR, they raised the bias up to 432 kilohertz. It turns out on ordinary audio tape that that's about the point of diminishing returns. And although there have been a few custom-built tape machines that use higher bias frequencies, I don't think there was ever a production machine that did. And you're getting into fractions of a dB of improvement at that point. So it really kind of amounts to not worth the trouble.
Okay.
Does that answer the question?
It seemed like it to me.
And yes, to look at the recent question, the THD of the bias is really important, particularly second harmonic, because bias that has second harmonic will make a much noisier recording than one that doesn't have second harmonic. So it's important to have spectrally pure bias. But
okay,
most machines that weren't of professional grade anyway, that weren't malfunctioning, generally had a pretty good solution to that problem.
There was also a question, could you do your transfers at slower speeds so that the head bandwidth isn't so critical?
Yes, and we have done that on occasion. One of the questions we get asked is, can you do this with any degree of success on a regular tape machine that doesn't have super wide bandwidth electronics and a very narrow gap head? And the answer is sometimes. If you slow the tape down, it helps you if you have limited bandwidth in the electronics of the tape machine. It does not change the relationship between it doesn't change the loss caused by the width of the head gap, because that's a wavelength problem. That's not a frequency problem. So you're still going to have that. And if you happen to have a bias frequency on the tape that's right where the notch caused by the width of the gap is, then there's nothing you can do to change the speed that's ever going to get you bias to come out of that head. If you have a machine with electronics that roll off at 60 or 70 kilohertz and you've got 100 kilohertz bias, you slow the tape down to half speed, yeah, you can maybe get some bias out of it. On an ATR, which has pretty good bandwidth in the electronics, we've actually gotten 120 kilohertz bias off an ATR without the special electronics. Now, if we had the special electronics, we'd have better signal to noise ratio, but we got enough to work with.
Hey, Robert Pavitas says lower speeds would give a lot more phase shift in the bass. Yeah?
Yes, but we can correct for that problem. And if you're talking about the plangent electronics, well, of course, we don't have to slow it down there, but one of the things when I built the plangent electronics, it has DC servos rather than coupling capacitors. And the low frequency limit of the electronics is about 0.05 hertz. So that's low enough that the electronics contribute virtually no phase shift down to 20 hertz. Now, on a real tape machine, particularly one that is older and has more phase shift at low frequencies, then yes, slowing it down and speeding it up digitally is going to sound different unless you have phase compensation that's good enough to compensate for what the electronics did to you when you slowed it down.
Okay, good questions and comments, everybody.
All right. So
before we move on, here's another one that relates to that. It's surprising that THD of the bias makes the noise worse. If higher bias frequency gives lower noise, wouldn't adding harmonics make the average of the bias components be at a higher frequency and thus give you lower noise?
That's a much debated question, but the simple answer is that adding second harmonic is essentially equivalent to adding, or any even harmonic is essentially equivalent to adding DC to the bias. And that will make it noisier. If you add odd harmonics, it's not harmful. Whether it's helpful is an interesting question, but I don't have any good examples. I've never really tested that to find out whether it's helpful or not. It's generally difficult to generate a signal that has no even harmonics and only odd harmonics. So it would be kind of difficult to build that and test it unless you synthesized it digitally.
Mm-hmm.
Once you can do that, you might as well just go to a higher bias frequency and be done with it.
Robert Cochran says it's the symmetry of the bias that is important.
Correct. And
yeah, okay.
Adding the even harmonics screws up the symmetry.
Yeah.
Causes the problem.
Good question, Simeon. Thanks, John.
So moving on, since we're going to be looking at bias recovered from a real tape, one of the questions is, how do I see the bias? And in the beginning, when we only had 192K sample rate converters, I had to have some way to have a spectrum analyzer that wasn't tens of thousands of dollars and showed me frequencies well above what I could see from the audio converter. So this is what I use. It's a picoscope, PC oscilloscope, plugs into a USB port on the computer, and has a nice spectrum analyzer display. And one of the things I'm going to show you here is a little demonstration using artificially modulated signals that show you a couple of important characteristics of what the bias is going to look like. So we want to go back to here. Now we want to go back to here. We want to add this. So that's 100 kilohertz signal coming from a digital function generator, which I can FM modulate. And this now shows you the frequency deviation, 200 hertz, and the modulating frequency, which is 10 hertz. So this is typically what you would see with low frequency WoW and Flutter on a tape machine. If you just had, Flutter that was 10 hertz, that's what you're going to see on the spectrum analyzer. The carriers just moving back and forth. And if you know anything about FM modulation, the number of sidebands depends on something called the modulation index. And the modulation index is the deviation divided by the modulating frequency. So for low frequencies, you've got lots of sidebands. And if I had enough resolution in the spectrum analyzer, which I don't, what you'd see inside those two vertical lines is many, many, many 10 hertz sidebands. And of course, with real Flutter, we have much higher frequencies. So now we're going to start increasing the frequency of the Flutter. We're now up to 200 hertz. Now you can start to see individual sidebands, and there are a number of them. And I'm going to reduce the deviation a little bit because typically the higher frequency Flutter components are usually lower amplitude, fortunately, because otherwise we'd have a whole lot of sidebands we'd have to capture and deal with. So if we go back to the modulating frequency and we keep turning it up, eventually we reach the point where we have only a single significant sideband when this settles down, because there's a lot of averaging in the spectrum analyzer. So now we have 910 hertz modulating frequency and 50 hertz frequency deviation, which is actually probably higher than you would have for a real Flutter component at that frequency. And we've only got two sidebands that we really have to worry about. If you could dig far enough down into the noise, the others are there. You can just see one of them poking up above the noise floor there. But the effect of cutting them off is pretty close to insignificant. So the reason I'm showing you this is because when we recover a bias signal, we have to decide what bandwidth we have to use to filter it, to separate it from all the other garbage and noise that it's surrounded by. And that requires us to know both what's happening at low frequencies and what's happening at high frequencies and the highest Flutter frequency that we hope to be able to correct. Because in this case, if we thought we could make corrections up to nearly a kilohertz, then we'd have to have something over plus or minus 1 kilohertz bandwidth when we recovered the signal. And if we go back down in frequency, to 10 hertz, and we go back to deviation, which is maybe typical of bias, which is 200 hertz at that point, that's a lot narrower signal. So if we only needed to recover Flutter components up to 50, 60 hertz, then we could use a much narrower filter. So that's why I'm showing you this with test signals, so that it's maybe a little more obvious than when we start looking at real bias signals. Any questions about that before I move on here?
Not seeing any.
Okay. Let me see what I've got next here. Well, we're just about getting down to time to deal with the real tape machine here.
Great.
And I'll go back to this. Oops, wrong thing. I'll get there eventually. If I just had some production crew on this show, it would run a lot smoother, but I'm it.
We're a low budget operation.
That's
What can I
right.
say?
So one of the things you have to worry about is tape guidance. Because as I said earlier, if you can't keep the tape flat against the head and keep it from weaving back and forth, you got big trouble. And we typically, do most of our transfers on an ATR. One of the things some people don't know about ATR tape guides is that if you draw a straight line across the bottom two tape guides, left and right, and you measure from that line to the top center tape guide, it's actually several thousandths of an inch less than the width of the tape. And so the tape is actually being forced into a curve as it goes through the head block. And this works, or it did work pretty well when they were using nice new tape that was nice and flexible. When you have old tape that's starting to get stiff, or in some cases was slid over with, not so happy. And I've actually gotten to the point where I typically run with a 2mm shim under this top center guide, which brings the spacing up to just about nominal tape width. And in extreme cases, I've had to go to a 4mm shim because the tape was so stiff that it actually curled and jumped off either the left or right tape guide. So that's just an illustration of some of the kinds of problems we run into when we start dealing with these old tapes.
John Mack asks, what filter bandwidth do you normally wind up using?
To recover the bias?
Mac?
Typically somewhere between 100 hertz and a kilohertz.
Mac, did that answer your question? Not sure.
Right.
I would jump in there for just a second while John's setting up, and the bandwidth of the amount of swing that's going on obviously can be quite a bit more than a kilohertz. If the machine is deviating by several percent, then it may be as much as 3 to 5 kilohertz, and then there's a noise reduction that has to be done in order to be able to get that straightened out. But if it's
That's true. Yes. If you have that kind of problem, then you obviously have to include the drift in the speed drift in the tape machine as well in the filter bandwidth, which does increase the necessary bandwidth.
Do you really want to geek out on that? Google Carson's rule.
Google what?
Carson's rule. It discusses the necessary bandwidth to recover the sidebands that John is talking about based on a particular gut modulation index. And typically, like what we're doing, if we want to do 100 hertz flutter, typically it's plus or minus 100 hertz. It's a pretty narrow. The modulation index is pretty close to 1 at these lower frequencies and lower deviations.
All right, thanks.
So this is going to take just a second while I switch my setup around here. Okay. So now what we're looking at, well, I should describe what we have in the Plangent box in a little more detail. We're looking at the flat output from the head, which has been high pass filtered so that it contains only frequencies where there's likely to be bias. And this is what we see coming out of that output. And if you can't read the scale on the spectrum analyzer, that's 50 kilohertz, 100 kilohertz, all the way up to 300 kilohertz. And at the moment, the tape machine is powered up. The electronics are powered up, but the tape is not loaded. That is, it's not under tension. The real motor system on the machine is not active. And we see some little pieces of digital garbage that come from the tape machine. And one of the sources of that digital garbage, as we'll see later, is the real motors on an ATR, which are controlled by a pulse width modulation driver that operates at 28.8 kilohertz. The other source is the control panel with the time display on it, because the time display is multiplexed and it generates lots of digital garbage. And if I hold that up next to the head, that's the control box there with the display turned on. You can see on the spectrum analyzer that life gets a whole lot worse. So my control box actually has a switch that enables me to turn off the display, which I do when I'm doing a transfer. And if I come back to the slides, oh, did that again. Eventually I'll learn. By the time I'm done with this show, I'll be really good at this.
On the road.
Yep. So here we have the control box showing the display on, and here we have it with it off. You also see that I've wrapped the cable with copper foil tape. And if you look at my tape machine, you'll see an empty spot here where the control panel normally resides. And even with the display off, it can't afford to be there because it's too close to the repro head. So it lives underneath the machine. And I turn the timer on when I need it and turn it off when I'm doing the final transfer. So now we'll load up the tape. Turn this on. If we go back to the spectrum analyzer. Oh, sorry, wrong thing. You can see that it got a little noisier. And one of my rainy day projects is to totally rebuild the real motor drive system in an ATR so that it doesn't generate that garbage. But so far, I haven't had enough rainy days to do it. So we live with it and hope that the bias ends up somewhere in between the pieces of garbage in a space where it's reasonably clean. So the next question would be, so how do you find the bias on the tape? And I'm just going to wind back a little way here.
Bob Kavanaugh suggests you move here to work on this because we have a lot more rainy days than you do.
Well, all depends on one's definition of rainy day, I guess. In the literal sense, I'm not sure that would help, but in the metaphorical sense, I should be able to arrange it here. It just hasn't happened yet.
Yes.
Okay, so here we go. And let's see, is audio turned up? You'll love what's on this tape. I should explain where this tape came from. Obviously, I can't take a valuable client master tape and put it on the machine and do this kind of demo with it, because that's not the sort of thing you're supposed to do with valuable client master tapes. However, this tape is it's not a first generation tape, it's a second generation copy of a master from a major record company, which I won't name, and made in 1959. And it was defective. A very good friend of mine worked at this major record company. And when this was judged defective and would otherwise have been headed for the trash can, he took it home, probably intending to use it for blank tape, but it got put in his garage and surfaced 50 years later when he was moving into a retirement home and we were cleaning out his garage. So I took it home and having no idea what was on it, put it up on the tape machine and went, oh, look, a 1959 recording that's other than the lousy recording, lousy music that's on it. It's a typical recording from that period and therefore perfect for demonstrating what we're about to see here. So that's where the tape came from. Go back to our spectrum analyzer. Now, are you guys hearing that audio at low level?
Yes.
Okay. I won't turn it up too far because it would get to, well, let's just say I wouldn't want to listen to that at high level. And here we can see indeed that we have bias. So now we know where it is. And if I adjust the azimuth, you can see the level change. Oh, there it is. Getting there. So somewhere about there, we got reasonable bias. So now we kind of know where that is. And since I can't really show you this live, it's about 94 kilohertz. So now, let's see, I have to move over to here. Pardon me 1 second while I reset the video here. Come on. And slightly down. There we go. So now we see what's on the front of the Plangent box here. Oops. It's where we can see the buttons. There we go. So we have one button, it's labeled 2448, and that just changes the output frequency from 48,000 to 24,000. The top line says FN, and I can select a digit with the left-right buttons and increment or decrement it. So what I want to do is to set this to somewhere close to the bias frequency. And there are two outputs on the front of the box. One of them says raw bias out, and that's the signal we've been looking at on the spectrum analyzer. And the other one says mixed bias out, and that's the one that's converted to 24 kilohertz. So if we go back over here, and I switch the display on the spectrum analyzer, so it's now centered at 24 kilohertz. There we go. Play the tape. And that's not exactly at 24 kilohertz. So this, you now see the insert there. And I can adjust the frequency here until the number displayed on the box is a really close match to the actual bias frequency. And it's not perfect, but it's pretty close. And then if I get another piece of video here. This, no, this. There we go. So the next thing I have is I wanted a way to measure the level of the recovered bias more precisely than I could do on the spectrum analyzer, because the spectrum analyzer is heavily averaged and doesn't respond very fast, and it's hard to read the peak level very accurately. So the 24 kilohertz output of the Plangent box drives a fairly narrow bandpass filter. It's about 400 hertz wide at 24 kilohertz. And that is displayed on a meter where I can read it. And that is right here. And yes, it says Heathkit, and the meter movement and the case are Heathkit, but I can assure you that the guts are no longer, having been replaced with something much more modern. So if we go back to the point where we see the tape recorder and the insert, and I insert the azimuth adjust wrench. Wrong way. And eventually we reach a point where it starts going off the other side. And then what you want to do is adjust it to the point where it's as stable as you can get it to be. Somewhere right about there, maybe. Considering that that's recovering 94 kilohertz off a tape made in 1959, that's not too bad, I think.
That looks great.
Very good.
So now we're actually ready to do a transfer. Let me just, we're almost at the point where I want to do that here. That's about where we want to start. So here we have the DAW set up with 3 tracks, 2 tracks of audio, and another track recording the bias. And some of you may be looking at these meters and going, that's a lot of noise. That's because we're actually recording the flat signal coming off the head. And these days, on tapes that do not have noise reduction, that's actually what we record. And in order to listen to it, we have a digital equalizer that has the tape EQ. And that's what you're hearing, is the flat signal from the tape that's gone through this EQ. So in order to do this transfer, I didn't have to put up the alignment tape and align the frequency response. I did earlier put up an alignment tape and set the two channels to be identical level. But I have previously transferred all the necessary alignment tapes using this setup, and I have those files for reference. And I've used those to create equalization curves that are appropriate for each of those equalization types. And just for giggles, I'll wind back a little here and play you some of what you just heard without the EQ. So that's what's actually going to tape.
What are the different things we're hearing here?
Huh?
What are the different, there were several different tonalities in there.
Well, I switched out the equalizer. So with the equalizer out, I'll play this condition again. This is no EQ. This is the signal we're actually recording. And the signal from a tape head is predominantly high frequencies because as a result of the nature of the tape head, the response rises at 6 dB per octave until you get to the point where losses in the head and the tape become significant and the response starts to flatten out, which is why what you heard there has no bass in it. And if I switch the EQ back in, does that make it clear?
I think so. It
Yes.
pointed out that the screen is a little blurry, but you're clicking a button there that is switching the EQ in and out.
Well, the EQ is a plug-in on
Yeah.
the master output of the DAW, which is what we're listening to.
Right.
And so I click the button that turns the plug-in off, and I hear what's actually being recorded. And with the plug-in enabled, which is the current condition, then you hear the signal that sounds like it ought to be coming out of a real tape recorder, the way we would want to hear it.
Yeah.
Yeah, one
Okay,
has
thanks.
got just the pre-emphasis on it, and the other one has been de-emphasized by the plugin.
Right.
It's basically NAB coming from the plugin. But what comes off the head is just off the head, which gives a hell of a lot cleaner high frequency response for the bias aspect of it, and also enables some tricks that can be done to the NAB curve to make it more accurate and to phase linearize it.
Yeah, because we can make a digital EQ that compensates for inaccuracies in the head and imperfect cases where the losses in the tape don't perfectly match the EQ that's normally used in an analog equalizer. So we can make it considerably flatter than most tape machines that use analog EQs.
All right.
So here we go. Click the record button, hit play. Lovely music, isn't it? Sounds like what you hear in an elevator. Anyway, I'm not going to subject you to an enormous amount of that because I don't need to demonstrate what we're going to demonstrate here. But it is still recording, and I will unload the tape at the end here before I stop it. So now we can actually look at that signal, get the right thing loaded here.
So this is the first step in the Plangent process. Am I getting that right?
Making this transfer, correct.
Yes. Okay.
If I had sat here for half an hour and transferred that whole reel of tape, I would have the files that I would send to Jamie.
Okay.
Okay. Where did it put my files? There it is. Okay. So here we see a spectrogram of what I got in the bias file. And you can see several other pieces of garbage here. The other interesting thing that I didn't mention, and this is more obvious I'll show you this later, never mind. I was going to show you scrape Flutter, but I have another illustration of that that's better. And at the end, this is after the tape stopped. So you can certainly see here that the noise from the tape is definitely higher than system noise. And this is the point where I unloaded the tape and turned off the real motor system. So this is what I'd love to get rid of and haven't got rid of yet. And whatever this is, that keeps going. That's not coming from the tape machine. I don't know where that comes from.
I'm not sure what you're pointing at when you say this.
Well, if you look, can you see my cursor wiggling around?
Oh, just barely. It's
okay.
It's in away from the file on the left. It's in the blue on the right.
Unfortunately,
right?
I have no better way to point at it.
Yeah.
Let me make this a little more obvious here. I brighten this up a little bit. You can now see, because zoom kind of butchers this.
Yes. Yes.
Now you can probably see right here, there's a horizontal trace.
Yes.
It carries on and it stops right about there.
Yes.
So that comes from the real motor system in the tape machine. And anything that stops, come on, cursor back in the right place, there, right at this boundary, that's the point where I stop the tape.
Okay.
And John, just to interject I don't know if everybody knows what a spectral analysis is, but basically vertical is frequency and horizontal is time. So,
right, and brightness and color are amplitude.
Right, so the red is a much higher level than the blue, which is lower level.
And you can see a scale over here on the right, which, although you can't read the numbers, shows you at least the progression from blue through green, through yellow, through violet into white. And I can zoom in on this. And ooh, look at that.
Red. Yeah.
Shows you how stable this machine wasn't. So all those little wiggles, that's what we're going to take out. What else do I have to say here? Scrape Flutter. Oh yeah, I was going to show you the Scrape Flutter. I just have to find the right file here. Does anybody know what Scrape Flutter is?
Yeah, I don't know.
Well, normally Flutter is created by usually rotating components which come in contact with the tape. So if, for example, the capstan shaft is not perfectly round or slightly off center, then you'll get a change in speed that relates to the rotational rate of the capstan. The same thing for any other rotating component that the tape moves over. And you get noise from balls and ball races and bearings. But Scrape Flutter is kind of a different animal. Scrape Flutter occurs at fairly high frequencies, typically something in the 3 to 5 kilohertz range. And it's the result of the rough surface of the tape passing over the rough surface of the head. And you have stick-slip friction, and the tape actually vibrates longitudinally as if the head were bowing a violin string, and actually makes the tape speed change at somewhere between 3 and 5 kilohertz. Modern machines have in either 1 or 2 little rollers in between the heads. If we go back to the slides, actually you can see that in the picture of the ATR head block here. There. So right there, if you can see what I'm pointing at with the cursor, is a Scrape Flutterizer. And that's a rather small roller, which has unbelievably precise bearings with a metal shaft and a ruby bearing. And the additional mass of this coupled to the tape breaks up the resonance, which would otherwise occur between the record head and the repro head, and gets rid of that high frequency resonance. Early tape machines like the Ampex 350, 351, 300 did not have this, and they had Scrape Flutter.
Thank you.
So where was I? Oh yes, I was looking for the example that shows you what that looks like in the spectrogram.
Thank you for that, John.
Right.
My mic wasn't on.
Okay, here we go. This. So here's the recording we get if I can record at 384K sample rate. And this was done earlier today because I really can't afford to take the time during this to do all the switchover necessary to go from one to the other. And the line, I have to make this a little brighter, don't I? because what I see is not what you quite see on Zoom. There we go. The line you see about in the middle, and this is showing you left channel on the top, right channel on the bottom. The audio is the little squiggly stuff way down around the bottom. And the bias is the line that's up around the middle. If we zoom in on it, that's a little too much. There we go. And we wait for number crunching to occur. Here you see the red line, which is the center frequency of the bias. And if you, it's hard to see on this, I'll have to show it to you on the spectrum analyzer. There we go. There's a nice spectrum analyzer picture. And that is scrape flutter. And here we are at about 94,300 for the center of the bias. And this is at about 90,876. So it's about 4 kilohertz. This little band of noise right around 4 kilohertz. And that, of course, generates sidebands on all of the musical components, which are 4 kilohertz away from the particular component you're concerned with. And yes, that is audible. And in a few cases, we have enough signal to noise ratio that we can actually take it out. If we have less signal to noise ratio, we can't. But and I think that about brings me to question time.
Hey, John, can you clarify more what you just said about the signal to noise ratio and taking out the scrape flutter? How's that different from the rest of the processing, I guess?
It's actually not different from the rest of the processing. In this case, it's, if you look at, let's go back to the spectrum analyzer here. And let's see if it's a little bigger so we can see it better. There we go. By the time you get over here all the way on the left, this is just random noise, probably mostly tape noise. And we need a certain amount of signal to noise in order to get a clean FM demodulation. Otherwise, if we have that noise breaking through into our demodulated signal, we end up introducing flutter during the correction process that wasn't actually on the original tape as a result of the noise that we let through. So we have to be very careful not to let that happen. So although we're not going to describe this in detail, we have developed a fairly good set of metrics that says how much signal to noise ratio we have to have for a particular bandwidth in order to guarantee that what we're picking up is only usable flutter signals that we ought to be correcting, and that we're not introducing any of the noise that is trying to sneak in. And in this case, this is really marginal. If we tried to correct that, it might not get better. If we had another 10 dB of signal to noise ratio out here, we could probably fix it. Does that answer your question, at least partially?
Not exactly, but I'm not going to dwell on it.
Well, think of an FM broadcast station. What happens to the FM broadcast station when you're out in your car and you drive further and further away from the transmitter? For a long time, you don't hear much. It just sounds normal. But eventually, when you get to the fringe area, you start to hear shh in the background. because the carrier from the radio station gets really weak and the noise starts to break through. So the analogy here is this is the carrier from the radio station, and this is all the background noise. And this has to be enough louder than the background noise that we don't hear the background noise.
Anything that isn't Flutter that we actually demodulate and put in the control signal actually induces Flutter. So what John is saying is that when you've got something that has this little amount of signal to noise ratio on it, which is really only 10 dB for these components, this component you could do all day long, but these guys, which are kind of wispy and they're coming and going, and they're risky at this stage because there's a fair amount of noise around them, and that noise is now going to come in as a time frequency modulation of the audio. It's going to actually remodulate it into Flutter that responds to this kind of Gaussian noise. So if these are strong as hell, as they were, like for example on the Presley, which I should probably, if I can dig out the picture of it, the scrape Flutter were up in here. I mean, and that one we could really do.
Yeah, I mean, those had scrape Flutter peaks that, probably had 25 dB signal to noise ratio on them.
Yeah, they were insane. So, that does that help explain it a little bit better?
Well, I guess I'm just confused how that's so. Normally you're going off the bias, and the scrape Flutter, you're going off something else for that?
Oh.
No. It's Flutter. It's just at a very different frequency range, but it's definitely changes in the tape speed, which occur at 4 kilohertz or thereabouts.
Yeah, put that bad boy up for just a second, John, if you could. All right, now here's how to visualize this, and this is actually what I saw at Howard.
We're actually looking at you, and
Yeah, I'm not seeing. There we go.
now you're back to me and looking at this.
All right, so this is what I saw at Howie Schwartz 19 million years ago. And if the machine were not moving at all, then all you would see would be the actual bias coming off the tape just as it was recorded perfectly as a single vertical spike. But the machine is moving down in pitch and up in pitch and down in pitch and up in pitch. So what you're seeing here is the average of that deviation. Now what you can't see in here until it's been played with a little bit more is to see what the actual, do you have a baseband, John, that shows the
I do have a baseband, actually.
That might be good to show, because
I have to go find that. Pardon me for 1 second here.
So basically what you're seeing is the entire aggregate amount of swing that's happening to the bias. And of course, since it's spending a little bit of time at 2500 kilohertz off center, there's going to be a visual representation of that at 2500 kilohertz off center. So what we're seeing is basically how much time did the machine spend at each speed that it's within that that range. Now, because of the fact that it's FM, which is really hard was hard for me initially to understand, is that it's what you're seeing actually is not just the deviation of the machine swinging up and down. You're seeing the sum and difference products. For example, let's say we've got a machine that's got a really lousy 60 hertz cog in its motor. All right, 60 hertz being the international standard for American anyway. And we put that an A440 flute in there. You would actually see a spread of from 440 to 500 and a spread from 440 to 380, because the sum and the differences are what the sidebands are. It's an intermodulation product. It's a multiplication. It's not an addition like you would get with harmonic distortion, where you get 440, 880, 1760, and on up the harmonic series. Here what's happening is that the multiplication of the flutter on top of the audio, or in this case the multiplication of the audio of the bias and the deviation, is where you'll see. That's why it is symmetrical the way it is, and that's why you'll see a lobe that's a 2.5 below and a lobe that's a 2.5 above. So What we're trying to do is capture enough bandwidth. Somebody asked earlier about how much bandwidth we try to use. We try to get as much bandwidth as it takes to get the useful information and no more. So we're not picking up schmutzy noise and putting that into the control signal. So make it
Okay, here we go.
That's good. That's much better. So
we shifted. Here we go. Shifted all the way over. I'm zoomed up a little too far here. There.
All right. So
this starts over here at about 3.16 hertz. That's the lowest major flutter component. Here's another major one at 20, almost 28. And interestingly, look at that. There's one at real close to 60.
It hurts, yeah.
And there's, of course, another one real close to 120, because on any machine that runs the real motors on power line voltage, you're going to have torque pulsations in the real motors that occur at predominantly twice the power line frequency. So any of those machines always have a significant 120 hertz flutter component in them. But I mean, look at all this. This machine was in really bad shape. This is all bearing garbage.
Yeah.
So just to be clear, this is an FFT analysis of the flutter components with each one of these spikes representing a specific frequency of flutter.
Correct.
Wow.
And normally what we'd see is you'd see a couple down here that are about like what you see. And the 60 and 120 would be maybe, 10, 15 dB lower than we see here. And then it would just gradually drop off as you went higher in frequency. But the fact that this continues with what are obviously real flutter components out to at least a kilohertz indicates that this machine had some seriously noisy bearings. And of course, nobody ever did wideband flutter measurements. So until they got to the point where you put your ear against the machine and went, God, that bearing's getting noisy, you didn't fix it.
On the other hand, Dale Manquin mentioned using a stethoscope quite a bit to listen to what was going on by listening to the deck plate.
That's a good method, but how many people did that either?
That's right. But he was a wild man about this. His website still exists, and it shows all of the flutter frequencies for all the balls and races and all of the bearings and every single possible moving component. And I think it's a 440, and it's bonkers.
Right, because one of his methods, which is the right way to do it, is if you want to know what caused one of these at least lower frequency flutter peaks, you measure the circumference of all the rotating elements in the tape path, and you figure out what the rotational rate is at your tape speed. And then you look for a component that's either at that frequency or possibly a multiple of that frequency.
Right.
And then when you want to really get complicated, you start analyzing the ball bearings, and you figure out what the size of the ball is and what the rotational rate of the ball ring is, and et cetera.
That's right. And another thing too is there's obviously a way to spoof the header on the digital file. I mean, if it's at 192, and I force it to play back at 1.92 meg, or actually the better way to do it is to downsample to 9600 and then force it to go to 96,000, which chips all the frequencies up by 10 times. It sounds like a machine shop. I mean, it literally sounds like a machine shop. It's definitely a piece of machinery wowing and whirring and clicking and whirring and clicking and clunking and doing all kinds of stuff. And unfortunately, that's multiplying against your audio. Yeah, Dan's point is right. That is absolutely just mechanical distortion, and goes back to something that I said very early on, which is that nobody was really, except some of the guys towards the end that were really working on these machines, had any idea how much. Oh, I love Studers. Okay, you do. Oh, I love Ampexes. Oh, you do. Yeah. Well, yeah. No, the electronics are a lot different. Actually, you know what? I defy you to listen to the E to E on a lot of these and tell which one's which. But as soon as you press play on the transport or record something and press play on the transport, you're hearing all this mechanical inculcated crap that's in it. And that's a lot of what you're hearing when you hear the signature sound of a particular machine. Crazy assertion, but happens to be real.
And all of this analysis is from examining the bias signal.
Yes. Yeah, that's a Flutter plot. It's actually a combination of the original machine and the playback machine, of course.
Right.
But the playback machine being a well-maintained ATR is a whole lot cleaner than what you see here. So this is predominantly the original recorder.
So you're using a known playback device to identify issues with the original recording device?
Well,
I
mean, in a sense, it doesn't matter what's produced by the original machine and the playback machine, because they are equally well corrected by this process.
Right.
But if you wanted to know what was the original machine and what wasn't, then I would have to do a Flutter measurement on the ATR and plot it out and set it side by side with this. And you would be able to see certain components that might be visible in this, but at very low levels, and say, oh yeah, that came from the ATR.
Okay. Is it possible, Alex asked the question a little bit ago, is it possible nowadays to make a mechanical transport that doesn't have any of this stuff? Or is it inherent?
Any? No.
Yeah.
You can make a lot less, but
yeah.
None?
Run it through Plangent, and there won't be anything there left. That's the thing that's really insane, is these all disappear. If the signal to noise ratio is good enough, what's the level of that first the 28 hertz one, John? How many minus dB is that?
I'm sorry?
The 28 hertz flutter, what's the level of that?
Minus 71 and a half.
Minus 71 and a half. It's about what's that? Minus 60 would be 0.1, so it's a little bit under that. That would go to nothing. That would go to zero. You wouldn't see it. Everything from 0 up to probably in the mid hundreds, 200 would be just completely gone, and then there might be little fringes of the stuff above, but no, it would be pretty much just demolished. Do you have one that's DWOW, John? I should have put one of those together.
No, I didn't have time to do the DWOW, but if you wanted to do that and post it as an example, we could do that.
I will. Yeah, I've got some of those that are prefab. So that's that. Let's see, somebody should get in touch with Dale's heirs to make arrangements to harvest the site and pay for it to remain online.
There's a few things that are missing from the site, like his famous spreadsheets that don't seem to be there anymore.
Yeah, Luke, if you can find those, I mean, you're really good at this kind of stuff. If you find, it was so comprehensive. I mean, it was so insane how much detail there was there. And a lot of the text was basic review of what John has been saying about modulation index and FM, and the formulas for FM are on there, for how to do an FM demodulation are there, sine, cosine, arctangent, blah, blah, blah. But there was a really comprehensive spreadsheet of what all those frequencies of all those little ball bearings and all that little stuff was, and it was just fascinating.
And by the way, if you want to see the actual waveform of this signal, here it is.
Yeah.
So this shows you can see it wiggle, see the frequency change in the machine. And
I'm not seeing any wiggling. Is it supposed to
you're
be
not?
moving?
No, but scan from left to right.
Yes.
And you'll see it's dropping toward the center, and then it goes up, and then it comes down again, and then it goes up again.
Yeah.
And that's the speed change over time in the machine. Slower than what we can see on the spectrum analyzer. And all the little fast stuff is what we did see on the spectrum analyzer. If I really zoom in, you'll see that that's a pretty messy looking signal. Got all kinds of high frequency garbage on it. And this is, well, we've seen machines this bad before, but the majority of what we do isn't quite this nasty to start out with.
Will be their incentives to remove themselves from the process. Mortality. All right.
And if I low pass filter this, let's see, low pass. I get rid of all the high frequency garbage. Now you can see much more clearly some of the lower frequency repetitive components of the flutter.
Yes.
So there you have it. And given that we're coming up on 3 hours.
Yeah.
This is tremendous. What a
job,
discovery and a fix.
It works. Yeah, it's funny. It's not new either. It's been around since 2003.
Huh.
But it's a matter of, you know, what a shitty salesman I guess I am or something. But it's just really intriguing how hard a sell it is to. I mean, I've heard everything from "Who are you to think you could improve my work?" And one of the famous engineers said that to me at one point. He said, "Who the hell are you to think you could improve what I did?" And lovable Al Schmidt said, "What are you talking about? You're fixing the machine. Fixing him would be a lot harder." So, I certainly had my share of, getting beat up by the big guys over the years. But one by one, we prevailed. We've done well with, with the client. We haven't lost a client yet. I pissed off a couple along the way, but that was, that's inevitable. They're artists. They're difficult sometimes, and I can be too. But none of them have left. Generally speaking, it's a happy technology. It is expensive. Somebody mentioned earlier that the amount of intensive work that goes into doing this is like, and they're like, why the fuck can't I just press play? Yeah, well, you can, but you're not going to get this.
Well, I mean, just to start with, think of how accurately you have to set the azimuth in order to recover these high frequency signals with any stability.
Yeah.
Mm-hmm.
Yeah. I mean, one of these simple pieces of math that I learned from John and from others is that, 15 kilohertz at 15,000 cycles at 15 IPS, you're about 1,000 samples, 1,000 cycles per inch. And that means that you're going to get half. You have to be able to split that in half in order to be able to get full level on it, which means on the oldest machines, they had to have a 0.5 mil or 500 microinch head. Typical of, I guess we were talking about the Bruce Botnick's ATR was 135 microinches. So that's going to get but look back at the 15,000 gives you, you get a 500. Okay, now we're going to go to 150.
Well, I mean, here's the wavelength table again.
Yeah. Yeah, it's easier for me to there's one number that isn't there, which is real easy, which is 15 IPS, 15 kilohertz. This is 1 mil. So you've got a 0.5 mil in order to be able to get it
right. But if you look at 16 at 937, it's damn close.
Yeah, it is damn close. And you multiply that by 10, and now you're starting to talk about a head that's, way, way finer. There you go, 75 microinches, 200 kilohertz. That's the film heads that we had made for the guys in LA for their Sondor Dubbers, tended to be about 75 microinches, and they would pick up 200 kilohertz, and 6 tracks of that without gap scatter, and they're all capable of maintaining azimuth. It's no joke. You get a better transfer. My God, I mean, I would assert that there are very few people, and I don't think there's anybody in the world that can do as good a job as John does. I mean, there's plenty of people who are extremely good transfer engineers. I mean, you're on Tal Miller is awesome. There's a lot of guys that are really, really good, but nobody has dove into it as hard as John has, and Really,
No,
really.
you haven't seen some of the instrumentation we have to use on the difficult jobs, because
Yeah,
this one would have been easy.
yeah, yeah, yeah. And you know, it's like why? Well, to me, it comes back to that comment by Jim Keltner. How come Hal Blaine swings so much harder in the Plangent version than he does in the original? And it's not hype. That's got nothing to do with sales. I couldn't have paid him $1 million. He wouldn't have said anything, you know, like that. And it was completely unexpected. But he's right. The performance is really, really, really sacrosanct. And anything that gets in the way of that is going to be putting a distance between the listener and the original performance. Is one of the things, just to be polemical for a second. One of the problems that I run into with having discussions about the budgets that are involved with Iron Mountain, in particular. Somebody mentioned Iron Mountain earlier, and you know they're working very, very hard to come up with a comprehensive method to store the tapes, transfer the tapes on site, never see them again. But I'm not sure that they're willing to go to this length to get the kind of quality. And unfortunately, that means that some of the stuff gets frozen in digital aspic at a level that's less than ideal. Because one thing about this, it's a downside of it. It needs the tape. You need the tape. Yeah.
And the only possible saving grace is that sometimes they capture bias accidentally, and it can be fixed later.
Yeah, that's true. Yeah.
There were a couple of questions that came up. One is, does the A to D and D to A have an effect on this at all? The question was, is the source colored, which I think
other than the question of whether you like the sound of those particular converters, certainly they're all more than good enough to have no effect on the defluttering process.
Not much. I mean, one of them we ran into, which I don't want to get into the names of the manufacturers, but one of them has a very, very gentle anti-aliasing filter, which meant that at 150 kilohertz, 140 kilohertz might be X phase, and 160 kilohertz might be 20 degrees away from that because of the equalization and because of the filter. And if the sidebands if they're not symmetrical, again, if the level's asymmetrical on the two sides, you won't get as good a result. So, and another one, it's really a heartbreaker because it's a gorgeous sounding piece of Pacific Microsonics Model 2, which, you know, there's a hell of a lot of stuff was done on a Model 2. A lot of the legacy stuff was done on a Model 2, and they're hesitant to ever go back and redo it. The damn thing sounded fabulous. But no matter what, if you were at 192, it still rolled off at 44 kilohertz, 48 kilohertz. And by 50, it was dead. So anything that was transferred with a Model 2 needed a sidecar of some sort to pick off. I mean, we've done things with the Model 2. We've done them for the Grateful Dead, but there's always a third track that's straight into Pro Tools. You know, so yeah, most of the time it's going to be good enough. The Mytechs are great. The Prisms are terrific. Glasser, we do a lot of work with Dave Glasser. He's all Prism. Just did something in London with emerging setup that was a little tricky, but managed to make it work. So that's the answer to that.
Another question, what are some of the harder transfer problems that you've had to solve?
Well, we have our own transport, so we really don't have to worry about that too much.
Transfer, I misspoke. Transfer issues.
Any particular transfers that were a pain in the ass, John? Other than,
well, the ones that are, I think, the most time-consuming to deal with are ones that have a lot of azimuth shift in the original recording, and where that's enough to considerably affect the stability of the recovered bias. And when you get one of those tapes, you know, if the bias was relatively stable, you know, I can just sort of twist the Allen wrench and go, that's the center. And on the tape like I have here, that would be good enough. I could just play the whole reel and I wouldn't have to tweak anything. On one of the ones where it's got the azimuth swimming back and forth, it's maybe moving so far that you got to get the azimuth really dead centered in between those two swings so that you have the absolute maximum stability on the bias. And that can take a long time. And it may result in the tape having to be done in separate segments, because if that was done on a machine that changed tape tension over the length of the reel, then the nature of the azimuth shift may shift with the tape tension. So, I mean, I can get 10 minutes into the reel and go, that's not good enough anymore. Got to stop. You know, another 15 minutes of screwing around and trying to get the azimuth set to the new level, do another 10 minutes. Those are the painful ones.
Okay, great. Thank you. Another question, what corner of the record industry, the people who own the recordings, the old recordings now, what part of them are you finding are actually prepared to spend the time and money to do the transfers with this sort of care? Are you seeing any part of the industry that's more prepared? I'm assuming that the fast buck artists are not.
You know, that's a great question. Often it's the artists that control their own catalog. I mean, you know, Legacy doesn't tell John Landau what to do. John Landau tells them what to do. You know, so if they want something for Bruce, then I don't have to sweat, you know, whether or not that's going to get approved. Legacy may not be thrilled about it, but they can't do anything about it. Also, one of the things that's interesting there is Legacy does an awful lot in-house, and that's a thing that we bump into a lot, is the original team. And you must respect the original team, particularly like Neil Young's guys. I mean, John Nowland was just unbelievably good at those tape transfers through a Pacific Microsonic, by the way. They sound fabulous. He was really good, and they are great, great sounding transfers. And so do you go back and reinvent that wheel? Well, you know, Neil was kind of against that for quite a while, except for some screwball shit that he had that had problems. There was a 1970 concert that was in rough shape. We just did a demo cassette that needed some work, and a film, Young Shakespeare, that just came out. That was kind of cool too, because they had a 15 IPS copy of the mag, and I could see the mag's bias on it. That rarely happens, but the mag was like 52 kilohertz, and it came screaming through on this 15 IPS copy, so we were able to skip back and get them in sync with the original video very easily. It's a Dutch film crew that did a concert with him, and he's now on board. He effectively owns his catalog. Queen owns their catalog. We've done a lot with them. Brian May's in control of that. The Grateful Dead obviously has a tremendous amount of influence over Rhino. Rhino, that's one of their biggest reissue acts. They still sell 10,000 units of American Beauty every month. So where the artist has the control, the Woody Guthrie thing, the foundation had control. Obviously, Nora Guthrie had control of her dad's assets. That's generally speaking a walk in the park if you can get to the right person. You know,
Concert by the Sea. It was another one.
Concert by the Sea. Exactly. That was the niece of Errol Garner's manager. Ended up with all of those assets before they donated them to, I think it was Case Western, and so we had no problem. Have had no problem there. What's tougher is, you know, like how am I supposed to find Giles Martin? You know, one of the things that is maddening about this is that I know that they're using a lot of time compression software to try to demix their old 4-tracks. They've got them all. They've got everything. So they've got a 4-track that was combined to one track on another 4-track, and then that was combined to a third 4-track, and like they would love to be able to separate that all out. And there's no better way to do that than to use our bias tracking method to be absolutely positive that you're getting everything out in sync. I mean, there's a California Girls, actually. If you listen to California Girls, it's in stereo. It's kind of sad because the track and the sweetening and the vocals wander away from each other in a few places. It's the best that they could do, hand syncing the machines together. I don't know how to get hold of the Beatles guys. The standing offer to anybody, I'll give $10,000 to the charity of their choice if they can find me 15 minutes with Giles Martin. But so the answer is yes and no. Where you can get to them and make a point, it's not that hard to sell once they've heard it.
Of course, the first stereo remix of California Girls was great, and then it was when they redid it, that was the one that was out of sync.
Yeah, is that what happened? I don't, I know it's all over the place, and it's the quality of it. Actually, the quality of the transfers is fairly good. I mean, it's it's more high fidelity than that Fender 12s at the beginning. Barney Kessel and them. It really is crystalline, but as soon as the band kicks, it just wanders all over the place. And I called Lynette, and I was like, dude, come on. We could do this. This would be really, really easy. And he's like, well, I don't think they'll let me go back to the original analog assets.
No, that was a political thing. It was done before Lynette was involved, and then he redid it.
Yeah, and just not to be too much of a dick about it, but also Kevin has really stopped that. I went to visit him, and there was
we're getting off track here a little.
Whole bunch of masters that were there that were Beach Boy masters, and it was just tough to get any traction. So
that was a great answer, and we've got a whole bunch of questions coming in.
Okay.
So thank you.
Mm-hmm.
Chris Myring, who points out that it's after 5 a.m. his time, but he's still been fascinated by this.
Oh, good.
Asks, what you've pointed out so far is that you're working on 2-track recordings. Do you do multi-track, and if so, what machines do you favor for that kind of recovery? Multi-track recovery.
Yes, it's really easy in the case of a live recording where all tracks are in record at the same time and they're all derived from the same master bias oscillator, which is usually the case on a live recording. There may be some patches here and there where they've jumped in. I've seen a couple things that artists have picked a few things later, but most of the time those are really easy. Done very, very few full-on multi-tracks that had a lot of edits and a lot of punch-ins in it. There's one famous one, which was Bruce Springsteen's Promise record, which was a 3-minute song that he wrote about an argument he was having back when he was in litigation with his ex-manager. And that had string overdubs, it had guitar overdubs. The basics were, the basics were all off of one oscillator. They were all off in one pass, so those were easy. But walking everything else in, again, Luke, we had a conform that came from Clear Mountain that was a mixed version, and we were able to sync it up with his original Total Recall and give it back to him. So when he pressed play on his SSL, it conformed. But that was a hell of a lot of work. John has magnificently rebuilt an MM1200 that happens to be our favorite machine of all. And this crazy machine was capable of doing a 30 IPS pass and then backing up and doing a 15 IPS pass, and they stayed together. I just doubled the frequency, the sample rate of the 15 to get it back to the 30 and played them against each other, and they were dead on.
And I'm equipped to do a half-inch, 2, 3, and 4-track in addition to the quarter-inch stuff. So anything that's more than 4-track half-inch, we got to go to somebody else and use their studio, take our equipment over there and hook it up to their multi-track, but we do that.
Yeah.
Okay, and Matt Perkins asked a question that I think might have been answered in your last answer. Is the bias signal taken from both tracks summed or just one?
Well, the answer to that is yes.
Yeah.
So whatever works.
Exactly. Yeah. Because of the, going back to the thing about the guidance, the center bias.
Well, let me back up a little bit. The original method that I demonstrated tonight, I have to make a choice to take the bias either from left or right on a 2-track tape. And so in that case, we only used to have one bias signal. But once we started recording at 384K sample rate, now we have bias from both channels. And that is useful in some respects.
Yeah. It's quite useful in some respects, and it's quite frustrating in others, because the the amount of what's odd is that there's what would be considered to be wow and flutters. Luke is asking about azimuth, also explanation of azimuth. Azimuth is how out of true is the tape on a moment-to-moment basis. Is it perpendicular to the gap, or is it swinging axially? That's one of the things you set up. You want to be absolutely sure that you're as perpendicular to the original recording with your head, not necessarily perpendicular to
Well,
the
I would
world.
say you're parallel to the original recording, actually.
Well, the gap has to be perpendicular to the travel of the tape.
Correct. But the recording is a vertical stripe across the tape. So if you think of the recording as being the vertical stripe, then the head's parallel to it.
Yeah, we could certainly do that. And if you look at the offset between the two sides and whether or not that's vertical or not. So anyway, in any event, it has to be orthogonal with.
In other words, the angle of the recording on the tape has to perfectly match the angle of the gap that's trying to reproduce it.
That's right. And one would think that would be a fixed deal that would not change, other than just the vagaries of how the guidance system of the machine is working and whether or not it's kissing that center guide correctly and so on. Actually, the original recording will swivel enough, if you will, that is a considerable differential in wow and flutter between the left channel and the right channel. So we can knock the left channel down to nothing, and the right channel will be damn close. It'll be probably 92% of the performance of the other channel. Summing them together you'd think would be a good idea, but actually what you end up with the kind of an amalgamation of the error that's in both of them, and sometimes it's better, sometimes it isn't. If it's a very, very noisy signal, one of the tricks that I've done is I'll take both channels and rely on the fact that the signal to noise ratio of the wow and flutter actually gets a lot better at lower frequencies. The higher the frequency of the flutter, the more you have to have good signal to noise to do anything with it. So in some cases, I'll take both sides and sum them together, drop them by 6 dB, and then meld in one side for the low frequency stuff, and end up with a better result than would be from one side or another. It's a kind of a complicated answer, but yes, to the extent that we can,
But we couldn't start doing that until we got to the ability to record bias on both channels at the same time, which is
till my text came
only a couple of years ago.
Yeah.
Okay. Any classical projects been done with this?
Mm-hmm. Yeah, the Mercury Living Presence. We did some stuff for Tommy a while back. Yeah. Did a really, really nice Copeland third, which is the Fanfare of the Common Man. Terrific Eastman Wind Ensemble thing that it was Mussorgsky Hindemith and Stravinsky, and that's a fabulous. The Marcel Dupré organ, the entire catalog that Mercury had on him. Some other things.
But I must say the classical tapes definitely take the prize for maximum number of edits needing to be repaired.
Yeah.
Because you can have a classical reel that's got, 40 edits in it.
Wow. Okay.
Those guys with razor blades were real aces back in those days.
I'm going to skip Alex's question about historical recording practices in interest of time here. He also asks, have any of the original recording artists listened to your transfers? And if so, what was their reaction?
Yeah. They have. Yeah. I mean, there isn't anything that John Astley, who is the chief archivist for The Who, there is nothing that they released that Pete Townsend hasn't heard. And if Pete doesn't like something, it doesn't happen. I personal story, I suffered through a number of years where between the time that Bob Ludwig and us did the Springsteen stuff and transferred it and processed it, and it was a while to get an approval out of him. It was a couple of years, actually, because of one thing after another. Excuse me. And it's the kind of thing where we sent him a CD rep in Australia, and he left it in the hotel. Excuse me. So that was another 6 months. But yeah, everybody's heard it.
Great.
Yeah, they have to. Excuse me. I gotta get some more.
Robert Pettis has a question about how he uploads his demonstration file about bias artifact to the Dropbox.
Just
I guess
drag
he
and drop it
tried.
onto the. Just drag and drop it onto the window.
Okay. And Robert, contact us if that doesn't work, and we'll figure out a way to
Should
do
be able
that.
to. If not, I might have to. He should be able to with the link that we provided. That should allow him to be able to get around the fact that he can't edit it. But if not, let me know and I'll take care of that another way. You can WeTransfer it. He can also WeTransfer it to Howarth at Mac.com. That's probably easier.
Okay. Any other questions? I think we're at the end of that.